Hi, everyone. Thank you for joining us for the Young Persons Lecture Competition in Canada. My name is Max Edgington. I am the Highly Qualified Personnel Coordinator for the Macdonald Institute. The Macdonald Institute is committed to supporting IOM3's Young Persons Lecture Competition, and we're happy to have invited contestants from around Canada to compete in our national competition. The Young Persons Lecture Competition is an excellent opportunity for researchers up to 28 years old to demonstrate their research on materials, minerals, mining, packaging, clay technology, wood science, or engineering related subjects in a 12 to 15-minute talk. The competition enables students to improve their presentation skills, showcase their research, and represent Canada at the Young Persons World Lecture Competition. Before we continue, I'd like to acknowledge where we are situated, especially considering today's competition, which includes partners who are spread out across different traditional lands. While we are all working digitally, many, if not all of us, reside on Indigenous land. Personally, living on the lands of the Cataraqui, what we now call Kingston, I am in the territory of the Haudenosaunee, Anishinaabe, and Huron-Wendat peoples. Reconciliation to me is honoring treaties, acknowledging Indigenous rights and title, and one way in which I can contribute to reconciliation. While I acknowledge the small victories, such as the new floating Indigenous Learning Center in Toronto, named Wigmawam Chi-Chamang, I also acknowledge the violence of colonialism and understand its present existence in our society. Violent and hateful acts are still carried out against Indigenous peoples. I speak today not only as a representative of the Macdonald Institute, but as a settler whose Swedish and British ancestors colonized these lands many generations ago. The land I'm using today has provided me with the necessities to live, with shelter during the pandemic, and countless other benefits, and I'm eternally grateful for that. Today, we have 9 exciting presentations from across Canada and 3 judges to determine our national final winner. I'd like to take a moment to introduce our judges panel, who we will hear from afterwards with the question and answer period for the contestants. Charlotte Gibson is an assistant professor in intelligent mining systems in the Robert M. Buchan Department of Mining. Her PhD is in mineral processing from Queen's University. Her research is focused on improving the flotation process and making it more energy efficient, as well as understanding how the flotation process can be applied to the concentration of minerals that are critical in battery application. Charles Niabese is our second judge and the Vice President of Business Development and Commercialization for the Center of Excellence in Mining Innovation. Charles holds a Bachelor's of Mining Engineering and an MBA, and endeavors to create long-term value through commercialization, revenue generation, leveraging funds, networking, collaboration for organizations and clients by identifying business development opportunities with both the public and private client segments. Lastly, our final judge is Martin Jones, who is the Repair Technical Coordinator at Rolls-Royce and the chair of the Student and Early Career Committee at IOM3. Martin holds a Master's of Engineering in Aerospace Materials and is also reading for his PhD with the University of Sheffield. Martin's role at Rolls-Royce looks to develop strategic repair technologies and to support current repair capability acquisition programs. Martin's specialty is in both additive and welding processes. Now I'd like to dial back to the session and to briefly summarize the events of today. Between 10 a.m. and 1:10 p.m., we will be inviting our YPLC contestants to present. Each presentation will be accompanied by 1 question from each judge. And at 1:10, we will begin our judges' deliberation process and decide the national winner. To start the day, our first presentation is with Hannah Ramsay, whose talk is titled Silver Clusters, Small Material, Big Potential. If possible, Hannah, could you unmute, turn your video on and share your slides?
Yes, I'll do that now.
Thanks, Hannah.
Oh, I just have to be allowed to share.
Oh, right. There you go, anytime.
Perfect. All right, so hello everyone. I'm excited to get things kicked off today. My name is Hannah Ramsay and I'm an MD PhD candidate in Dr. Kevin Stempelkowski's group in the chemistry department at Queen's University. My talk is about the material I study, silver clusters, which are a small material with big potential, which hopefully I'll show you today. Humans have always been fascinated with materials, and what seems to first catch our attention are materials that are really big. Whether it's the Big Apple just outside of Kingston, the astoundingly tall CN Tower, or the Grand Canyon, these attractions are really interesting to us and as a result are very well visited, or as we say in science, very well studied. As technology improves and as advancements pave the way towards new innovations, we become increasingly captivated with the small. Before we knew about bacteria, doctors didn't even wash their hands before surgery, which is pretty gross. And though a chest at the size of a quarter may not serve a functional purpose, it's pretty cool to look at. So what about a material that can do both, be unprecedentedly small and serve a unique purpose? It's argued that this idea was first addressed in Richard Feynman's lecture titled "There's Plenty of Room at the Bottom," which was given in 1959. In this speech, Feynman discussed the importance of manipulating and controlling things on a small scale and discussed the knowledge gap that existed about very small materials. He described how properties appear to change depending on scale and proposed that in the future, it would be possible to directly manipulate and control individual atoms. Though his lecture did not make much of a splash at the time, it's now regarded as the earliest discussion of nanotechnology and paved the way for the amazing field of nanoscience that still has so much potential to be realized. The Nobel Prize-winning invention of the scanning tunneling microscope in the 1980s by IBM allowed scientists to see materials at an unprecedented atomic level at the nanoscale, which is shown here. On the nanoscale, we talk about materials in terms of nanometers. A nanometer is a billionth of a meter. Can I get everyone to blink their eyes? So I can't see you, but I'll assume you did it. For comparison, in terms of time, a single blink of an eye is about a billionth of a year. So hopefully you can appreciate just how small these materials are. I also recently learned as a fun fact that your fingernails actually grow at 1 nanometer every second. The materials I research are nanoscale in size and are approximately 1 nanometer in diameter. As Feynman and many other scientists noted, properties of materials do change at this nanoscale. For instance, you all know gold. Some of you might be wearing gold right now. Gold is yellow and shiny and conducts electricity. If you had a gold ring, for example, and you took it and you cut it in half, each half would still have these same properties, such as color, melting point, and conductivity. Even if the ring were cut up many more times, down to the size of a grain of sand, these properties would stay the same. However, if this grain-sized piece of gold were cut in half many more times, until the pieces were under 100 nanometers in size, which is roughly the width of a human hair, then these properties would start to change. A great example of this can be found in medieval stained glass windows, and arguably the artists that created them, though unaware of it at the time, were some of the first nanotechnologists. These artists would trap gold nanoparticles in glass and generate a ruby red color in their windows. They would also trap silver for a deep yellow color. These days, many more colors and properties can be realized by changing the size and shape of these particles. The materials I study are called silver clusters, and though you would expect that they would be silver in color, due to these nanoscale changes in properties, they are generally orange, pink, or yellow. And here you can see a representation of what these silver clusters look like when they're dissolved in water. To break down the name given to this material, silver is the metal that this material is made of, which is represented by the chemical symbol Ag, and these clusters are comprised of silver atoms. Silver was actually one of the first 5 metals discovered by humans, so we've known about it for a long time. And then we have clusters. So a cluster is a group of similar things positioned or occurring closely together, as can be seen in a bunch of grapes or a group of flowers, for instance. And so here is a very general representation of the structure of my silver clusters. The core is made up entirely of silver atoms, which are shown in red, and the core is stabilized by capping molecules, also called ligands, which are represented here by the letter R. These ligands typically contain the element sulfur, which has the chemical symbol S, which they use to bind to the metal core. Many different ligands can be bound to the core, allowing for very specific binding to occur. Now here we have the actual structure of these clusters. The top left shows the metal core, comprised only of metal, and the middle image shows the metal core stabilized by sulfur-containing capping molecules like we talked about before. The structure is further stabilized by staples of both the metal and ligand that bind to the metal core in 2 places, creating this very stable, intertwined, and complicating looking structure that you can see on the bottom right. So how are these clusters made? The typical synthesis involves combining silver and sulfur-containing ligands, which are represented here by RSH, together under specific conditions, and then using a reducing agent, such as sodium borohydride, to reduce silver with a 1+ charge to silver 0. This is evidenced by a color change from clear to yellow to black and results in the formation of these clusters. The issue with this synthesis is that it cannot be controlled after this reducing agent is added, which can lead to the formation of many different products, shown here by solutions of different colors, that are difficult to isolate and characterize. In my work, I have developed a new way to synthesize these clusters that's able to overcome this problem. Instead of forming clusters with a reducing agent, I use high energy ultraviolet light and a photoinitiator that's able to absorb this light to form clusters. The photoinitiator I use is the molecule OmniRad 2959, which is shown here. Now the reaction can be controlled by turning on and off this light, achieving purer products and more readily allowing for the discovery of new clusters. In these images, you can see the result of dozens of different experiments producing different products by changing the concentration of silver and the ligand used, and by changing the total light irradiation time. Due to their small size and structure, these clusters have a number of interesting properties, but the most interesting are their optical properties, which are displayed when clusters interact with light. When stimulated with light, these clusters can release heat or fluoresce, depending on what wavelength of light is used. They're photostable, which means they can exhibit these effects repeatedly and over long periods of time. They also display interesting nonlinear optical properties, which is a fancy way of saying that they are great imaging agents, but we'll get back to that later. Silver has long been known to have antibacterial properties, and these clusters have been found to exhibit this property as well. These clusters are biocompatible and have been shown to be non-toxic to human cells. Finally, and perhaps most importantly, these clusters are highly tunable, which means the number of metal atoms, ligands, and accordingly shape and size can be precisely controlled. By controlling these variables, you're able to generate clusters of specific sizes with specific properties that can be used for specific applications, and we call these clusters atomically precise. The ultimate goal of my project is to build a library of these clusters, represented here with 3 different kinds of ligand groups in 3 different colors, that are able to specifically bind and recognize different proteins, ions, and binding sites in the body. I will then work to identify the most fluorescent and biocompatible of these clusters for future studies in imaging and therapy. Other applications in addition to imaging and therapy include fighting infection, solar energy, and chemical sensing. But I wanted to give you a brief overview of how this material can be used for bioimaging and photodynamic therapy, as this is the current focus of my work. All right, so let's talk about light. The light filling the room you're in is what's referred to as visible light because it's what your eyes can see. Light waves are nanoscale size, and visible light waves are 400 to 700 nanometers in wavelength, which you can see on this diagram here. Most visible light doesn't penetrate the skin well, thank goodness, because we'd see each other walking around as skeletons. So what does penetrate the skin well? We can actually do a quick experiment right now to figure it out together. So if you take your phone flashlight, turn it on and hold it up to your hand, you can see that most of the light does not get through except for one color, which is red, even if it doesn't look super red here. And that's because longer wavelength, lower energy light, like red light and infrared light, are able to pass through biological tissues. This explains why silver clusters hold an advantage over traditional dyes that are used for imaging, many of which only absorb higher energy, such as blue light, which cannot pass through the skin. The complex chemical and electronic structure of clusters allows them to absorb infrared light, which can pass through the skin easily. This absorption leads to the red emission signal that you can see here, around 700 nanometers, to achieve high resolution imaging. This is why the study of what kind of light these clusters absorb and emit is extremely important. We study the fluorescence or emission of these clusters using a technique called excitation emission matrix spectroscopy, or EEM for short, because that's kind of a mouthful. Using EEM, we can look at the complete quantitative fluorescence profile of a given material. This is shown by this bird's eye view of a 3D fluorescence plot, where the x-axis is the energy of light you're firing at the sample, the y-axis is fluorescence, and the z-axis is intensity coming up from the graph. For instance, the red dots you see would be where the emission is most intense. If you take a vertical slice of this graph, you can see what the fluorescence of the samples looks like as you excite the cluster with light of a specific energy. For instance, if you fire blue light of 484 nanometers at the cluster, you get this emission signal shown on the right. So clusters can absorb infrared light and emit red light. What else can they do? Clusters can also absorb infrared light to produce reactive oxygen species. Reactive oxygen species create damage in cells, leading to cell death or apoptosis. When clusters are designed to accumulate specifically in cancer cells, this process can lead to cancer cell death and is therefore a very targeted form of cancer therapy. This process is also called photodynamic therapy. Through my research, I'm designing a cluster that can take advantage of both of these properties at once and work as both a therapeutic and diagnostic, or as it's called now, theranostic agent to deliver localized therapy. I'm excited to report that I have designed several new and unique clusters that are being tested for these properties right now with our collaborators in Toronto and are already showing promising cell uptake and biocompatibility. For all of these reasons and more, silver clusters are a small material with really big potential. So thank you so much for listening, and a big thank you to my professor, Dr. Stempelkowski, as well as my wonderful lab mates in our matching sweatpants here, as well as NSERC and other funding agencies. I just finished up my first year of medicine at Queen's, and I'm excited to continue to work towards realizing the clinical implications of these materials. So a big thank you to IOM3 and for all of you for listening, and I'm happy to take any questions at this time.
Thank you so much for quite the fantastic presentation, Hannah. What a fantastic dive into silver clusters. I would now like to invite our judges panel to ask questions, starting with Charlotte Gibson.
Thank you very much, Hannah, for the presentation. It was very interesting. A question for you. Is there any large scale or any current commercial applications of silver clusters, or what is are they being used right now, and what are they being used for?
So that's a really excellent question, and that is something we're trying to work towards. So this nanocluster technology is really new. It's sort of just picked up in the past couple of years. What's typically used, and you might have heard of before, is the use of silver nanoparticles or gold nanoparticles. And these, though they have been used, there are still some outstanding questions about their toxicity and exactly what materials comprise solutions of these particles. So it's not exactly known what they are, unlike these substances where you know exactly how many metal atoms and how many ligands are part of the structure. So we're designing these to address this problem. Larger scaling up hasn't happened yet. It's something that we're kind of starting out now with these studies. So starting out in cell models, and it would move to some animal models, and then hopefully it could move on to some trials, but we're sort of at the very beginning of something here. And yeah, similar technologies with bigger particles, to my knowledge, have moved along further and are being tested in sort of larger pig models right now, but this is just the beginning for this.
Okay, thank you so much.
Thanks, Charlotte. Now could I invite Charles to ask a question?
Thank Hannah, thank you for the presentation, and congratulations on entering med school. I know that's not easy, so congratulations for that. Hannah, I've had some exposure to something called nano beads that are used in mineral processing. Basically they create these nano beads, and these nano beads capture certain types of atoms, because certain types of atoms can bind to these nano beads. And it's a really neat way of extracting minerals from solution. But my question is, do you think that the nano clusters that you put in the library, is that something that can be patented? Can you put a patent on that? Is that something that you can put as an intellectual property? And that's sort of my question. That is, can you actually create an intellectual property of these nano clusters that you put in a library that can then have applications to different things moving forward?
Yeah, that's another excellent question. Again, we're at the sort of the very beginning of this, but so I've discovered several new materials so far, and these have been published in papers. So we sort of have the rights to having discovered these materials initially. And down the road, if we discover one that's super exciting, it could be one of the ones we already have that does exactly what we want it to do. I could see that being a possibility in the future. Obviously, the scalability is really important. We want something that we can make a lot of, that is very reproducible, that does what we want it to do. But right now, in the small scale in the lab, it's showing this potential. So I don't know a whole lot about patents and business, but this is something that will be very interesting to me if this takes off a little more as it progresses down the road.
Okay, thank you.
Thank you so much, Charles. Could I invite Martin for the last question?
Yeah, thank you, Max. And yeah, thank you, Hannah. That presentation was very interesting for those of us that were able to watch it uninterrupted then. So I guess my question is mainly around one of the applications that you touched on in your presentation around the targeted treatments. I'm just wondering if you could expand on what you see the potential advantages of this solution being over some of the others that are in development or even in use today.
Yeah, for sure. So I think the ability of these materials to function as both a diagnostic and therapeutic marker is really exciting. So you have a material that can specifically accumulate in cancer cells. They have increased vasculature. This leads to this sort of increased retention effects. You have these very small materials that can pass through tissues easily, accumulating in tumors, and then you're able to use light to excite these materials with infrared light to produce reactive oxygen species to kill the cell. So it's really exciting that you have this one material that can kind of produce this whole interface of effects just itself using some light. Existing materials that they use for this process are very expensive, so that's a limitation of those, or common isotopes they would use for imaging technologies are very expensive and difficult to produce. And then, like I said, you also have nanoparticles in this space, which have been shown to be toxic in a lot of instances, and it's not exactly known exactly what these materials are. And especially when you're putting something in the body and you're moving on to a clinical trial, you want to know exactly what you have so you can know exactly how it might degrade or change in the body. So these clusters offer an advantage in this way, along with that combined theranostic effect. So yeah, for all of these reasons, I'm super excited about it. And hopefully I got you guys a bit excited about it too.
Yeah, for sure. Thank you, Hannah.
So thank you, Martin. Thank you, Hannah, for your presentation. Great start. I would now like to invite our next speaker, Jinsong Xia, presenting magnetic activated carbon for efficient gold recovery. So when you're ready, Jinsong, please turn on your camera and begin sharing your presentation.
Okay, thanks, Max. So sorry for that I missed the introduction part. I had also some technical issues. So good morning, everyone. My name is Jinsong Xia. I'm a second-year PhD student at Mining Engineering, Queen's University. And the topic of my lecture is magnetic activated carbon for efficient gold recovery. The value of gold has been established in the human history for a very long time. And with the development of the technologies, gold has been playing a more and more important role in our daily lives. Actually, most of us use gold every day. Perhaps you don't believe me because you don't have a gold ring or gold necklace, but you may have a cell phone or a computer, and gold is always there. Usually used as connectors because of its great conductivity, malleability, and stability. And gold can also be used in other advanced technology areas as well, such as satellites and aircrafts. For example, gold coating can be used on satellites to reflect the infrared light and absorb the visible light. And gold can also be made into alloy with titanium to form one of the strongest materials in the world. And that can be used in aircrafts. And my favorite application of gold is the use of gold in medical applications. Just as Hannah's presentation, gold is very similar to silver, and gold nanoparticles are widely used in drug delivery, cancer treatment, gene therapy, and bioimaging. And all of these applications are very important to the developments of the medical researchers. So now that we know that gold is not only a valuable metal, but it's also a very useful and commonly used and important material for our daily lives and also for the technologies. But the question is, where do we get those gold? They are mostly from mining. Our world produces over 3,000 tons of gold every year. And with the improvement of the mining technologies, the way we mine gold has also improved a lot dramatically in the last few centuries. In today's lecture, I will firstly introduce how gold is mined nowadays, and then I will talk about the use of activated carbon in gold mining. And then I will introduce the idea of using magnetic activated carbon in the gold recovery process. And I will also share the outcomes and the future perspectives of this material. So how gold is mined nowadays? After they got the gold ore, which is the rock that contains gold, What they usually do is to crush and grind the gold ore first. And the purpose of this step is to liberate the gold, which can make the next leaching more efficient. Leaching is dissolving. Using leachate like aqueous cyanide solution, gold can be easily dissolved into the solution and become ions. So after the leaching step, the gold transferred from the solid state into the liquid state. But this isn't over. They still need to extract or recover the gold from the mining solution. And how to do that? They use activated carbon adsorption. Adding activated carbon into the gold solution, those gold ions can be adsorbed on the surface of the activated carbon. By doing so, they can separate the loaded carbon from the slurry by screening. And the loaded activated carbon will be treated as elution to dissolve the gold from the surface of the carbon. And this will produce a small volume and concentrated gold solution. And that gold solution will be sent for electrowinning. During the electrowinning, you can see that those gold ions will be reduced on the surface of the cathode. And they will take the cathode for rinsing, drying, melting, and pouring into the molds, and plus extra purification to get the final gold bar for the market. This is the very simplified flow sheet of the gold production. The real operations can be much more complicated than this. But from this flow sheet, you can see that activated carbon adsorption is a very important part in the gold production. But why they are using activated carbon and why activated carbon can do this work? There are a few reasons for that. And the first reason is that activated carbon has a very strong adsorption ability. This is because of its highly porous structure. And you can see that because of the high porosity of activated carbon, this material has a very high specific surface area. And because of the high surface area, this material has a high surface energy. And in order to reduce that surface energy, they tend to attract molecules or ions from the air or from the solution. This is why those activated carbon filters at your home can clean the water and the air for you. So this is the first reason. And the second reason is that activated carbon has a very good affinity to gold ions. It means that the gold ions will be attracted to the activated carbon. And activated carbon is able to recover the gold from a complex solution. So this is the second reason. And the third reason is that activated carbon is also a sustainable and economical material. It can be produced from all kinds of the organic resources and the waste. In fact, most of the waste in your kitchen can be used to produce activated carbon. So because of these reasons, activated carbon is widely used in the gold industry. And since it was introduced in the gold industry 50 years ago, this material has made a huge impact to the industry, and it greatly reduced the operation costs and improved the production efficiency. However, this technology is not perfect. There are some limits in this technology. The first limitation is the slow recovery rate. The current technology suffers from a very slow recovery rate, which is because which can be explained by this graph. In this graph, you can see that the gold recovery rate is decreasing with the increase of the carbon particle size. It means that the larger of the carbon particles, the slower the adsorption. But you can also see that in the industry, they always use this size range for the gold adsorption. What's the reason for that? It's simply because they need to separate the loaded carbon from the mining slurry by screening. If the carbon particles are too small, they cannot do that. So they have to sacrifice the recovery rate to achieve a better separation. So this is the first problem. And this also brings us to the second problem, which is the imperfect separation. As I mentioned before, the loaded carbon is separated from the mining slurry by screening. But screening is not a selective separation. Those screens may blind or break due to the extended use or excessive wear, and they need a frequent maintenance and replacement. And even with the frequent maintenance and replacement, there are still a lot of gold and carbon cannot be recovered during the process. So we have these problems and challenges in the current technology, and the low recovery rate and the poor separation. But in order to solve these problems, we proposed a material which is magnetic activated carbon. And I expect using magnetic activated carbon, it's able to recover gold at a higher recovery rate. And also it can provide easier separation, which is magnetic separation. And the use of this idea in gold recovery is like this. So these are the gold ions. After they are adsorbed under magnetic activated carbon, they can be separated from the solution with the external magnet. Comparing to the traditional separation technology, I believe this technology is much faster and more convenient, and it can reduce the complexities of the operations. But how to make a magnetic activated carbon? This is what I did. I added activated carbon powders into the iron precursor solution. And during a certain reaction, those iron ions will crystallize to form Fe3O4 magnetite nanoparticles within the pores of the activated carbon and also on the surface of the activated carbon as well. And because magnetite is a highly magnetic material, it will also make the final composite magnetic as well. This method is simple, low cost, and easy to scale up, and I believe it's suitable for the industry. So this is how this material looks like. You can see the activated carbon is covered with lots of iron oxide nanoparticles on the surface. And there are a lot of iron oxide nanoparticles in the pores as well. And this is a test of the magnetism of this material. You can see that those magnetic activated carbon are easily separated from the solution with the external magnet, and which is much more easier and more efficient than a traditional separation. With just 15 seconds, it can achieve a complete separation here. So now we know that this material is magnetic, but how does it work in the gold recovery? In order to evaluate a material for gold recovery, there are 3 key points. And the first is if it can adsorb the gold efficiently. And the second is if the gold adsorbed on the material can be efficiently eluted. And the third is that if the material is reusable. We don't want to make a material that can only be used just once. So based on these 3 points, I did 3 different experiments. And the first result is showing us this. You can see that comparing to the commercial activated carbon, magnetic activated carbon is able to recover the gold much faster, and it's able to recover 98% of the gold with just 2 hours, which proved that this material has a very good gold recovery efficiency. And the second result is the elution results. You can see that most of the gold adsorbed on the material can be efficiently eluted. And the elution efficiency of these tests were all above 95%. And then the last result is the reusability results. You can see that after 5 cycles, this material is still able to recover most of the gold from the solution. So it is reusable. So based on these results, we can say that this material is a good material for the gold recovery. And this is a very simple history of the gold production. You can see that before 1970s, back then there was no activated carbon used in the gold industry. And the gold production was limited because there was no good gold recovery technology. And since 1970s, activated carbon was introduced in the gold recovery technology. It boosted the gold production by increasing the gold production efficiency and reduced the operation costs. However, this technology has not been changed in the last 50 years. And I think maybe it's time to improve that. And I think maybe magnetic activated carbon is one of the future options. And I also think magnetic activated carbon can be used in other applications areas, such as water treatment. I think it can be used to remove the heavy metals from the water and also other impurities. I also think it can be used in chemical and pharmaceutical purification. And because activated carbon and iron oxide are both very good material for supercapacitors, so I believe this material can be used in energy storage area as well. And I also hope this material can be used in air purification to give us more clean air. So this is the end of my presentation. I would like to thank MyTech's Quorum, Agnico Eagle for funding this project, and also thank our hydrometallurgy group and our mining engineering department, and thank McDonald and IM3 institutions for organizing this competition, and thank all of you for being here and listening.
Thank you so much, Jinsong. Great presentation. Could I please invite Charlotte to ask the first question?
Hi, Jinsong. Thank you so much for the presentation. Very, very interesting work that you're doing. A quick question for you. Do you have any idea of what the addition of magnetizing the carbon might add, what type of operating costs that might add compared to the existing process where you have no pre-treatment of the activated carbon?
So thank you, Charlotte, for the question. And the price of the regular activated carbon is around 1 to 2 Canadian dollars per gram. And I believe the additional cost will be around $2 to $3 Canadian dollars per gram. This is calculated based on the lab scale, but I have no idea what's that going to be in the industrial scale. So. Okay,
yeah, thank you.
Thank you.
Thank you, Charlotte. Could I invite Charles for the next question?
Yes, thank you for the presentation. Just camera on. Thank you so much for the presentation. My question is concerning the absorption rate. Okay, so when you introduce sort of another variable into the activated carbon, and you spoke about how activated carbon is porous, and how that's a good thing. Does adding these ion components to the activated carbon reduce absorption in any way, and if so, what is the percentage?
Thank you for this question. It's a great question. Actually, it did because adding iron oxide into this composite, because iron oxide is also take up some of the weight of the material, and it didn't contribute to the adsorption ability. So it will reduce some of the capacities, but I think the adsorption rate can make up for that.
Thank you, Charles. Could I invite Martin for the last question?
Yes, thank you, and yeah, thank you for your presentation, Jinsong. I guess the aspect I was most interested in going through that was just wondering on what the environmental impact might be of adding in the iron oxide particles. Is it going to make the situation better or worse because you've got another fine scale particulate, obviously, that you're adding into the process?
Thank you for this question. It's a great question as well. I think for now, I only think this material in the gold industry, and I think it can only improve the efficiency of the gold production. I haven't thought about anything, and I don't expect this material can change things about the environment. But if we use this material for environment applications, for example, the water treatment, and I think it may have some contributions.
Thank you.
Thank you.
Thank you so much for your question, Martin. And great presentation, Jinsong. Thank you so much. I would like to invite our next speaker, David Patch, to present green synthesis of metal-treated textiles for antibacterial applications. So David, please turn on your camera, unmute your mic, and begin sharing when you're ready.
Okay, just to confirm everyone can see my screen?
Yeah, great, David.
Excellent. Thank you so much. Hello, everyone. Welcome. My name is David Patch, and today I'll be talking about my research looking at the green synthesis of metal-treated textiles for antibacterial materials. So before I get too far into it, just a little bit about me. I'm a PhD candidate at the Royal Military College of Canada under the supervision of Dr. Iris Koch and Dr. Kayla Weber. My personal interests include science outreach, education, and citizen science, as well as making science in general as accessible as possible. My research focus is looking at the release of emerging contaminants from commercial products. I started my graduate studies about 4 years ago, investigating the release of silver and copper from clothing into the environment. The research focus of our group has since shifted into investigating the release, transport, and remediation of new emerging contaminants, such as PFAS, explosives, and pharmaceuticals. However, I've always maintained an interest in high-performance metal-treated textiles for use in the healthcare settings. The science behind synthesizing high-performance metal textiles is amazing. By adding metal ions together with other reagents and heat, You can change the chemical form of the metals and bind them directly to the textile. Depending on the metal and the textile you use, the applications can be almost limitless. For example, high-performance metal textiles have been used in medical bandages to fight off bacterial and fungal infections, athletic clothing to inhibit odor-causing bacteria, air filters to reduce airborne pathogens, and water filters to eliminate germs. While all these applications are very exciting, there wasn't really a huge driving force for us to pursue research in this field. And then COVID happened. And well, as we all know, COVID is quite the driving force. It was at this point I had the idea, could I develop high-performance metal textiles for use in face masks? Face masks have been used for centuries to combat the spread of disease, especially during epidemics and pandemics. While the face mask has come quite a ways since being packed with herbs and worn by plague doctors, there is still a lot of ongoing research looking at ways to make face masks and other PPE more protective. I asked the question, what if I could improve face masks further by adding metals to self-sterilize the materials? Now, given my experience with the commercialization of other metal-treated textiles in the past, I knew I wasn't going to be the only one asking this question. And sure enough, within a few months of COVID starting, several metal-treated face masks entered the commercial markets. And just like in previous commercializations of metal-treated textiles, many of the products entered the market with next to no information as to how the materials are made, and if there were possible risks to the environment or people by using these materials. Without this information, these products that are meant to help protect people may end up causing more harm than good. With all this in mind, my project goal was then established. My goal was to develop metal-treated textiles for use in face masks to impart self-sterilizing abilities. The method itself should result in stable metal particles that are not released from the material during use or laundering. The next step was to identify what metals to use for this project. Fortunately, the ancient metallurgists, alchemists, and doctors have already done that work for me. Silver and copper are two metals that have been used since antiquity for the inhibition of bacterial and viral development. Both are used in commercial products today for bacterial and viral inhibition. And we're talking about metals, in particular copper and silver. The chemical form, also known as the speciation, size, and shape of the metal influences its characteristics dramatically. With a project goal in place and the metals identified, it's now time to plan out the project approach. It was decided that accomplishing this project in phases would be best to ensure the highest quality of science was being performed, while also ensuring I eventually got some time to sleep. So the focus of today's talk will be looking at phase one, the synthesis phase, which once again is to develop a method to incorporate metals into textiles to take advantage of the antibacterial and antiviral properties of silver and copper, respectively. So to do this, we investigated 24 different total synthesis trials across 8 different methods and 3 different types of metal precursors, silver, copper, or silver-copper together. Of our 8 methods, method 1 was a positive control where only the metal was added and no other chemical reagent. Next, in terms of decreasing environmentally friendliness, we investigated sodium bicarbonate in green tea, ammonia, sodium hydroxide and ammonia in 2 different ratios, and lastly, sodium borohydride. We identified these 24 methods by both identifying what's been performed and published in literature, as well as by identifying what kind of metal chemistry we could target when working with cotton cellulose textiles. For a little bit of a sneak peek as to the chemistry that's going on, I have this time-lapse video right here. So under this reaction, we've taken silver nitrate and reacted it with sodium bicarbonate in solution to form silver carbonate. In the presence of cellulose fabric or cotton, the silver carbonate is reduced to metallic silver, in the process oxidizing the terminal alcohol groups on the cellulose to carboxylic acids. Now, to investigate 24 different synthesis trials, we need an analytical To achieve this, we had fluorescence spectroscopy, which allows us to find the amount or total concentration of metal present on the textiles. We next used X-ray absorbance near edge structure, or Zane's analysis, to find the speciation of metal in the textiles. And lastly, we used scanning electron microscopy, or SEM, to find the size and shape or morphology of the metals in the textiles. And when we're investigating 24 different trials, we have to have an idea as to what our ideal synthesis method is. So with that in mind, the ideal synthesis method should have high amounts of silver and or copper present on the textile. This represents an efficient method that is uptaking as much of the metal from the solution as possible. Once the metal is on the textile, it should ideally be metallic silver, metallic copper, and or copper oxide. These three species of the metals are known to be very highly stable on textiles and while maintaining their antimicrobial and antiviral efficacy. Lastly, when looking at these particles, they should be spherical or semi-spherical in nature, and ideally less than 500 nanometers in size. This presents the ideal surface area to volume ratio to take advantage of the antimicrobial efficacy that occurs in the surface of the particles, while making sure that the overall method of the antibacterial effectiveness is as efficient as possible. So with this in mind, let's jump right into our XRF results, first starting off with our silver trials. So as you can see right here, on our x-axis, we have our 8 different treatments. On our y-axis, we have our concentration of silver in milligrams of silver per kilogram of textile. And the image we can see right here are the cotton textiles after synthesis. As we can see, methods 2, 5, and 6 resulted in the most amount of silver present on the textile, which we can see both by the bar graph, as well as the deep amber color present on the textiles. We can then shift to our copper trials. And once again, we can see very similar ideas in terms of the darkness of the textiles being correlated to the amount of copper present. Here we can see methods 5 and 7 result in the most amount of copper present, but all the methods resulted in some amount of copper binding up onto the textile. And lastly, we can take a look at our bimetallic textile, in which we take silver and copper and mix them together on the textile. Now, as you can see here, methods 2 and 4 through 6 and 8 resulted in considerable amounts of silver and copper binding onto the textile, which once again, we can see based on both the bar graph as well as the deepness of the color on the textiles themselves. Now that we know how much metal is in the textile, we need to identify what kind of metal it is or what the speciation of the metal is. To do this, we can use Zane's analysis, which will tell us the chemical speciation of the metals. In the top left corner and the top right corner, we have the silver and copper speciation data for the silver only and copper only trials. In the bottom left and bottom right corner, we have our silver and copper speciation for our bimetallic textile together. The biggest takeaways here is for our silver only trial, methods 2 and 5 through 8 result in all the metal present on the textile being elemental or metallic silver. However, all the methods resulted in some amount of metallic silver, so all the methods had at least some partial amount of success. For our copper only textile, we can see here that methods 4 through 8 resulted in most of the copper existing on the textile as copper oxide. When we shift our focus to our bimetallic textile, we see methods 2, 3, and 8 resulted in all the metal being present as metallic silver, but once again, all the methods had some amount of metallic silver, suggesting partial success at a minimum. And lastly, looking at our copper data for our bimetallic textile, we don't really see any big difference compared to the copper alone textile. We see methods 4 through 8 having most, if not all, of the copper being present as copper oxide. So now that we know how much metal is present, as well as the type of metal, we need to know what our metals look like. And as the saying goes, sometimes a picture is worth 1,000 words. So when we do SEM analysis of our textiles, something unexpected happened. When we looked at the surface treated textile, the silver treated textiles, we saw no surface formation of silver except in the sodium borohydride trial. In the copper treated textiles, we did see minimal surface formation of copper across all the trials. However, we didn't see as much metal as we were expecting. And for the high concentrations that we analyzed, we should have seen a lot more silver and a lot more copper, which asks ourselves the question, if it's not on the surface, where is it? Well, just like Christmas, sometimes the best stuff is actually inside. And unfortunately, unlike Christmas gifts, we can't really tear these open and look to see what's inside, but we can do the next best thing, which is taking the textiles and putting them in an oven at 550 degrees Celsius to burn off the cotton. And when we do that and do SEM analysis on the ash, we see the following image. So as we can see right here, we have spherical silver particles scattered throughout the ash surface. If we select an area and zoom in further for analysis, we can see a number of spherical particles of very similar size distributions all the way around this image. I could give you guys a few minutes to manually count and identify the diameters of these particles, but I thought I'd save you all some time and just do it myself. So using a software called ImageJ, I was able to count and determine the diameter of all the particles. And as you can see here, most of the particles exist between 100 and 500 nanometers in size, with some smaller amounts of particles being silver nanoparticles, less than 100 nanometers in size, and larger silver particles, 500 nanometers in size and larger. If we now shift to our copper treatment method under method 2, sodium bicarbonate, we see the images slightly different. Our particles overall look smaller, and they look semi-spherical in nature, unlike the very nice rounded spherical particles that our silver exhibited. If we do our image J analysis, we can confirm that. Our particle sizes are overall shifted smaller, and we see most of our particles between 0 and 300 nanometers in size, with a smaller amount being between 300 and 400 nanometers in size. Shifting now to our bimetallic textile with silver and copper together, performing image J on this is quite tricky because right off the bat, we can't tell what particles are silver and what particles are copper. Fortunately, we have another technique called energy dispersive X-ray spectroscopy, which allows us to identify the elemental composition of the metals present when you're doing SEM analysis. So if we overlay that EDX spectrum on here, we can see that most of the particles, in particular the larger ones, are silver as shown in red. And the smaller ones kind of decorating the surface are copper as shown in green. I realize I've thrown a lot of data at everyone here, so I'll just quickly summarize our main results and findings. If we first overlay the textiles that had the highest concentrations of metals across the different trials, we see here in purple that methods 2, 4, 5, 6, 7, and 8 resulted in at least high amounts of metals across one of the 3 treatments, if not more. If we then overlay the textiles that have the ideal metal speciation, we can see the textiles that now have both high concentrations of metal and the ideal metal speciation. If we then pick these textiles, we can identify which textiles are ideal to take forward to the next phase of research. Based on our findings here, we identified that sodium bicarbonate is a novel and green method for synthesizing silver and silver copper treated textiles based on the high concentrations of spherical metallic silver particles found. Sodium hydroxide is a novel and moderately green method for synthesizing silver, copper, and silver copper treated textiles based on the high concentrations of spherical metallic and semi-spherical copper oxide particles. And lastly, sodium borohydride did generate silver, copper, and silver copper treated textiles with the desired particle shape, size, and speciation, but did not achieve the high concentrations when compared to other methods, and it itself is a dangerous and toxic chemical to use. So with all of this in mind, the first phase of the research has been completed towards the development of stable, self-sterilizing textile materials. Completion of this project will result in multi-application reusable materials that will reduce the waste and costs associated with single-use items. The extent of self-sterilization may also allow for textiles that don't need to be laundered as frequently, preserving material longevity and saving water. These findings here will allow for improvements to face masks, PPE, hospital textiles, athletic clothing, water filtration technology, and so much more. I want to take this time to thank the Arthur B. McDonald Institute and IOM3 for hosting this competition. It's been an amazing opportunity to prepare my work for this stage and to present it alongside all the other amazing work that has been and will be presented here today. Lastly, I'd like to thank you, the audience, for being here and watching my presentation. Your attention and time has been a privilege. Thank you very much, and I would love to take any questions.
Thank you so much, David. Could I invite Charlotte to ask the first question?
Thank you, David. Very, very interesting work. I think you sort of touched on this at the very end of your presentation, but you're envisioning this to be used? So my first question is, are you envisioning this to be used mainly for single-use PPE or for reusable PPE? And if it is for reusable PPE, do you have any indication at this point whether or not the efficacy of the treatment of the materials or the textiles will decrease over time?
Thank you for the question. We are hoping that these will be used for reusable products. One of the big things that kind of struck out at us was that at the start of COVID, countries were ordering billions of single-use masks, and they were often entering into waterways and just polluting up rivers, oceans, and streams everywhere. So ideally, this technology will go towards reusable materials. In terms of the efficacy following multiple uses, we are going to be investigating that in phase 2 and 3, looking at how the stability and effectiveness of these textiles lasts over multiple washings and multiple uses. But we have not looked at that yet, no.
Okay, thanks.
Thank you.
Thanks so much, Charlotte. Charles, could I invite you to ask the next question?
Sure thing. Thank you, David. And David, to acknowledge your college. It's one of the best colleges in Canada. I think Ramsay is right up there.
Thank you very much.
You're most welcome. So my question is really concerning microfibers. You look in the news, you hear stories about, the ocean water, the riverways or the waterways are contaminated with this much microfibers. And what I'm wondering is any addition of, say, metals to these fibers going to make things worse environmentally, or is it going to make things better?
It's a great question. And it's one of the reasons why we picked cotton materials over something like polyester or nylon, because the cotton materials will hopefully eventually break down over time. Assuming they break down and the silver materials themselves are released into the environment, the research that I performed in my earlier graduate studies, as well as research I performed with our collaborators in the group, identified that once silver and copper are present in the environment, especially as particles, they are quickly oxidized, chlorinated, or sulfidized, in which case their reactivity and toxicity plummets dramatically. So overall, no, we don't believe that there will be any long-term risks of this technology to the environment, but that will be evaluated further in phases 2 and 3.
Thanks so much, Charles. Thanks, David. Could I invite Martin for the last question?
Yes, thank you. And thank you, David. Another very interesting presentation there.
Thank you.
I guess I just wanted to pick up on one of your conclusions, or your results rather. The difference between method 2 and method 3 was the addition of green tea. So firstly, why green tea? And then secondly, what do you think is driving quite a dramatic change in the addition of green tea? Because you're saying that method 2 was one of your best results, and yet green tea, it was the addition of green tea, it really just changed things quite significantly.
Yeah, absolutely. So we used green tea because in synthesizing nanoparticles themselves using a environmentally friendly method, you can often take a metal precursor and mix it with a green product like green tea, in which case the polyphenols, the tea, react up with the metals. We wanted to try it for this to see if it would result in some kind of finishing step or securing step on the textiles. But what ended up happening is as soon as you mix the silver and the green tea together, they react with each other before they had a chance to react with the cotton textile. And this was really great for identifying to us what mechanism was going on, suggesting that the reaction of silver and copper onto the textile was quite a slow reaction compared to using green tea. So to answer your question, out competition. The green tea outcompetes the cotton cellulose for binding sites with the silver.
Right, brilliant. Yeah, thank you, David.
Thank you so much.
Thanks so much, Martin. Great presentation, David. Really engaging. So I would like to now invite our next speaker, Brodie Moore, who will be presenting Studying Irradiation Creep Behavior of Nuclear Reactor Structural Components. So Brodie, whenever you're ready, please turn on your camera and begin sharing your screen.
Sounds good.
Thanks, Brodie.
There we go. All good. And you can see and hear me, see my screen?
Yeah, looks great.
Excellent. Okay, so good morning, everybody. My name is Brodie Moore. I'm a second-year PhD student at Queen's University. And today I'm going to be talking about what changes in a reactor, how we're studying irradiation creep behavior of nuclear reactor structural components. Oh, my bad. There we go. So to start things off, I'm going to give a quick background on nuclear power, why we're interested and how the research I'm presenting can affect the industry. Now, unfortunately, when I say the words nuclear power, the first thing that pops into a lot of people's mind is this guy and kind of big silo of bubbling green ooze. And that's kind of their limit of what their understanding of nuclear power is. So I always like to start things off with a couple quick rapid fire facts about why we're interested in nuclear power and why it's important. So number one, almost 60% of the electricity consumed in Ontario comes from nuclear power. Secondly, the Canadian nuclear power industry generates upwards of $6 billion in revenue every year. In addition to that, it's responsible for supporting and creating 21,000 direct jobs and over 50,000 indirectly. And finally, nuclear power produces 0 greenhouse gas emissions. So by contributing to nuclear power and the research I'm presenting, we are directly supporting Ontario power generation, jobs, and that overall shift to green energy. So moving on here, this is a schematic of a CANDU reactor. And you'll notice it is not a bubbling vat of green ooze. It is instead actually just kind of a very complicated way in which we boil water, we spin a turbine, and that turbine generates electricity, which goes to the grid. And so how we generate that power or that energy to boil the water is the nuclear reactor core right here, which looks something like this in real life. You can see some humans here for scale, and all these circles in the background here are the fuel channels, which look something like this. So we have our fuel bundles. They're surrounded by water, and then these two concentric tubes, which is kind of what we're focusing on today. These tubes are the pressure tube and the calandria tube. They're both made out of some zirconium alloy, as you can see. And the reason we focus on them is because due to their proximity to the fuel channel or the fuel bundle, they experience high levels of this phenomenon that we call a radiation creep. So what is a radiation creep? Well, it's very similar to regular creep or thermal creep as we normally refer to it. And for those of you who didn't do a undergraduate mechanical engineering, which is probably most of us, creep is basically just a gradual extension or deformation of material over a long period of time. So you take a piece of metal, you apply a load to it, and after several months or even years, it is slowly deformed. And creep is something that we have studied for a long time. It's well understood, the behavior, to the point where we can make graphs just like this for specific materials under specific loading conditions and temperatures, and we know how it's going to behave. And what we usually study and what we focus on is the central region right here, where this is the time where material spends most of its in-service life, as well as it has this nice linear slope that we're able to calculate for a material at a specific temperature. We call that slope the creep rate. And so determining this creep rate is actually very important for a lot of design processes and design parameters. We're using a lot of engineering calculations for things like safety factor and tolerances. So it's a very important number to determine for materials going to like a prolonged use, such as in a nuclear reactor. Unfortunately, when we take these materials and we put them in a high radioactive environment, such as a nuclear reactor, this understanding kind of goes out the window and it doesn't behave how it normally does. So here's a perfect example right here of some of this radiation creep. This is a fuel channel in a PWR reactor where you can see these normally straight fuel channels have a lot of bend in them and have deformed greatly over a number of years to the point where this is no longer safe in the reactor. They have to be replaced. That's a huge, huge overhead cost. And this is something that just needs to be avoided when we're designing and implementing materials in a high radioactive environment. So what's going on there? Like what happened? It turns out it's actually kind of a side effect of the nuclear reaction that's happening. I won't go into the big details about the chemistry or the physics behind this, but what's important to understand is what kicks off this reaction is a neutron interacting with our uranium atom. It splits, making energy, and that's how we generate our electricity, but also generates these other neutrons. And those neutrons go on and interact with other uranium atoms, continuing the process. But they also interact with the structural components like the pressure tube and the calandria tube I showed in the surrounding structure. And what happens there is as these neutrons interact with and collide with the atoms in the structural components, they can actually knock them away or displace the atoms. And we call this displacement damage, aptly named. And as this is happening all over the material, it can actually change the properties and change the behavior of the materials from how they normally behave outside of the reactor. And what that looks like graphically here is we have two plots. This purple line here is the exact same plot I showed before, where we have our standard creep and we know its behavior and how it should look like. We have our nice linear slope. This particular one was for zircaloy 2 at 300 degrees, 112 MPa. And when we take that exact same material and the exact same stress and temperature and put it in a reactor, now the only difference is it has a flux, meaning that's like the number of neutrons per second it's experiencing. It has this drastically increased creep rate. And it's important to note that how much this changes is greatly dependent on the temperature, greatly dependent on the stress, and the flux as well. So it's kind of a complicated problem. And it's very important that we understand what this change is, what this new radiation enhanced creep is for all the components we're putting in a reactor. It's important for reactor safety, lifetime extension of current reactors, as well as the design of future reactors. And so we need to go about understanding exactly how this creep rate is changing. And to make matters more complicated, it's not as simple as saying, okay, what's the temperature in this reactor, what's the stress, and what's the flux, because it's not the same. It's not a singular number. If we look at a fuel channel here. This is a cross section of one of those channels I showed before. If we look at the flux, even at any given point along this channel, we can see that the flux, again, that's the number of neutrons per meters per second, is not the same at any given point and can vary by up to 2 orders of magnitude. And the same goes for temperature and for stress. And that basically at any given point, we have these 3 different variables that all affect the creep behavior, and they're all different. So effectively, we have a different creep behavior at any given point. So in order to kind of tackle this problem, we need a systematic way of exploring this 3 variable scenario where we systematically explore temperature, stress, and the flux or the damage being caused by the reactor to see its effects on the creep rate. So how do we do that? If we had a nice small tiny reactor in a research lab, that'd be great. There's a few health concerns with that. And sorry, my phone is going off. I love spam calls. If we had a small reactor in our lab, that'd be a bit of a health concern. That'd be a problem. So instead, what we use is another fancy piece of equipment, which is a proton accelerator. This is a picture of the accelerator inside the RMTL facility at Queens. And what we do is using this accelerator, we can irradiate targets with high energy protons and basically simulate the conditions that are going on inside a reactor. We're recreating that displacement damage normally caused by neutrons, only now we're using protons that we have a much higher degree of control of, as well as it's in a controlled and safer environment in the lab. So now we're simulating our displacement damage. We need to also simulate our temperature and our stress. So to do that, I introduce the apparatus I've been working on the past few years of my life, the Proton Irradiation Tensile Rig, the PETR, as we like to call it. It's a uniaxial testing device designed for prolonged creep experiments in the reactor, in the accelerator. It has contact-free thermal measurements, and most importantly, it's designed for in-situ measurements, meaning that it is controlling the temperature and controlling the stress while the sample is being irradiated by the accelerator to closely mimic the conditions inside the reactor as possible. This is what it looks like implemented. Here's our vacuum chamber, and behind this concrete wall is that picture I showed before of the accelerator. And inside, we have our sample connected to our grip, supplying the load, and our LVDTs are where to take our strain measurements, effectively leading to our creep measurements eventually. So as I said, we want to use this PETR and accelerator combination to simulate the conditions inside a reactor as close as possible. So we want to compare to what's going on in standard reactors. We have our CANDU reactor here. This is the Canadian design, the picture I showed earlier, as well as a PWR. It's a slightly different, but otherwise very similar one, very popular in the States. And looking at our temperature ranges and our stress ranges, we can see that our PETR and accelerator combination is more than capable of reaching all those ranges. We're able to systematically look at, 300 degrees, 310 degrees, 320, etc., as well as our damage rates. So here, damage rates, this is that displacement damage I talked about. It's given in dPa, which just stands for displacements per atom. And that's just because we're comparing the amount of damage caused into material by either neutrons or protons. So we can do basically an apples to apples comparison as opposed to comparing the number of neutrons versus number of protons. So we have all our experimental parameters we can manipulate and choose. Now we're able to basically pick one and set up an experiment. So we can go to any point that we chose in our reactor here in our fuel channel, say this point or this point, and determine what's the flux, what's the temperature, what's the stress, and we can run a creep experiment using those parameters. And when we do that, it looks something like this, where we chose a 350 degrees and 55 MPa test. That's these red and orange lines. And the important line to look at is this blue one, which is our strain in which we get our creep rate out of at these parameters. So once we've done that, we can take our creep rate. Okay, there's a creep rate. And basically, we now know that the creep behavior at that particular point and those conditions for a reactor. So with a systematic approach, we can go through the various conditions, looking at what happens when we change temperature, what happens when we change stress and flux, etc., and determine the creep behavior of specific materials at those conditions, and ultimately determine the creep behavior for the whole system in the reactor condition. So to understand that is very important for reactor safety, lifetime extension, and also important for the design of future reactors. So to summarize, I talked about today. Within a nuclear reactor, there's dramatic changes to the structural behavior of the structure of materials in a reactor. To help work through this problem, the Peter was designed as an experimental apparatus to simulate the conditions and determine the in-situ behavior of these reactor materials. Developing this new understanding will lead to improvement of reactor safety, lifetime extension, and future reactor designs. And finally, improvements in the nuclear industry are beneficial to Canadian power generation, supporting jobs, and that overall shift towards green energy. So thank you very much. Thank you to all the staff at RMTL and the facility I work at, and my supervisor, Professor Mark Damon, and to everyone here in attendance. Thank you very much. And I'm happy to take any questions.
Thanks so much, Brodie. Could I please invite Charlotte to ask the first question?
Yeah, thanks, Brodie. Yeah, really great talk. Yeah, very interesting. I don't know anything really about nuclear power, so that was some good background for me. A question for you. Are there any major differences or any conditions that you are not able to simulate in the rig that you've developed compared to a nuclear reactor that might influence results in some way, whether it be major or in a minor way?
Oh, that's a very good question. So one of the key differences between the protons and the neutrons, like neutrons are what we're trying to emulate and protons are what we're using, the protons actually have a lot faster, maybe faster is wrong, but like a faster damage rate, meaning that we can achieve the same levels of damage much quicker, which is actually kind of beneficial in the sense that if we're doing a test, if you saw on the time scale on some of those, it can take thousands of hours. And if we're doing multiple 1,000-hour tests is a little, I don't want to sit through that. So if we're able to do these tests a lot faster, it's beneficial to us. It's just a matter of proving that even though we've done it faster, the kinetic effects are basically the same. So it's kind of, for that, we turn to a lot of the simulation guys in my research group. That's not my expertise, but it's kind of like a baseline that we have to ensure that, the damages that we're seeing is comparable to what is seen in a reactor.
Okay, thank you.
Thanks, Charlotte. Could I invite you to ask the next question, Charles?
Thank you, Brodie, for the presentation. You know what, I guess just to maybe agree with Charlotte, I mean, I'm not a nuclear power expert by any means, and thanks for bridging the knowledge gap. Look, I pay attention to what's happening in the nuclear power industry. In particular, there's a rover on Mars today that has a nuclear power plant on it. And, that power plant is miniaturized. It's supposed to last 14 years or so. Now, I know that, here on the planet, we're looking towards small modular nuclear reactors. And because of the scale of those reactors, I guess my question is, does scale matter when it comes to creep, irradiation creep? Are the smaller nuclear reactors safer? Do they have the same challenges with irradiation creep as you'd find in a sort of the Kouider reactor? If you can just comment on that, please.
That's a very good question. I would say that it's very similar in terms of the worries and what needs to go into it, in the sense that even on the smaller scale, creep is still an issue that we need to have this understanding of, that we know after X amount of years under this scenario, this is how the material will behave. It doesn't really matter if it's a small reactor or a large reactor. It's basically understanding that verifying, and we know that like after X amount of time, this is what the material will do and how it will behave. So I'd say it's equally as important on both scales.
Okay, thank you.
Thank you so much, Charles. Martin, could I ask you to ask the last question?
Indeed, thank you. And yeah, thank you, Brodie. Another really interesting presentation. And as somebody that has heard of some of these alloys before, I guess, so the Zirc 25 niobium and the Zircaloy 2 have obviously been around quite a long time now, in terms of their use in nuclear reactors. And the industry is quite reluctant for change for various reasons. So I'm just wondering if you envisage your work actually looking at developing new alloys that could maybe combat this challenge more effectively.
Yeah, so that's actually one of the great benefits of the Peter, is that it's made for just any material, in the sense that, so like when I'm doing all my initial testing, pressure tube material, Kouider tube. It's a little expensive. So all the materials that you break along the way. I started with just pure zirconium, meaning that like it's adaptable to use pure zirconium or a zircon alloy, or even a steel alloy or whatever we're interested in. So we're more than capable of doing tests on those materials. So I think that'd be, once this kind of endeavor is finished, I think that'd be a great thing to branch into. That'd be great if I could develop a new material that they want to use.
Yeah, fantastic. Well, yeah, keep his eyes open for that one. Cheers, Brodie.
Amazing. Thanks, Martin. And thanks, Brodie. Great presentation. I'm very, I'm very happy with all the presentations so far. Everyone's really, really engaging, and it's amazing to see the research you're all up to. For our next presenter, we're going to be introducing Artash Nath. So Artash, if you have your slides ready, please share screen, and I will start the timer. Amazing, I can see it. Thanks, Artash.
Hey, thanks. Hi, everyone. Good afternoon. My name is Artash, and I've been working on projects related to space, science, robotics, seismology, and most recently COVID-19 for the past 5 years. In fact, today I'm going to be talking to you about my work on using seismic vibrations to measure the effectiveness of COVID-19 lockdowns. By the way, I'm a grade 9 going to grade 10 student from Toronto, Canada. Now, in December 2019, the COVID-19 virus first emerged in China and quickly spread to countries all around the world. On 11th March 2020, the World Health Organization declared COVID-19 a global pandemic. This caused a cascading effect as countries around the world closed national borders and enforced lockdowns to stop human-to-human transmission of the virus. Canada was no different. Within a few weeks of the World Health Organization announcement, all Canadian provinces had enforced some sort of lockdown, closing non-essential travel, workplaces, businesses. In fact, even my school had turned online, and the Canada-US border had been closed. Now, these lockdowns are absolutely essential to stop human-to-human transmission of the virus, but they come with huge mental, social, economical, and political costs to our society. And these lockdowns are only effective if citizens actually comply with the legislations. So how can we measure the effectiveness of COVID-19 lockdowns in real time? Doing this would allow us to understand if the lockdown legislations are working at keeping people at home. I would also allow policymakers to enforce surgical lockdowns based on time and location to minimize the cost of the COVID-19 lockdowns. Now, to measure the changes in surface level human activity above the ground, I turn to the well-established field of seismic engineering. Seismic engineering has been going on for over 120 years, when the first seismic station was set up. Seismic engineering is the bedrock of modern economies and infrastructure, as all big engineering projects and buildings require planning based on seismological surveys, as they are, of course, built on the ground. Seismic stations are already a big part of public infrastructure in countries around the world. In Canada itself, there's over 200 seismic stations. And the best part is, new micro-seismic stations are already being embedded in urban societies, like Raspberry Shakes. And now they're becoming as ubiquitous as mobile phones. In fact, now even technology allows mobile phones to be used as seismic stations. Now, seismic stations are very, very sensitive to ground vibrations. And they're usually used to measure natural vibrations, like the ones from earthquakes and volcanoes. But they're so sensitive that when placed near urban areas, they can also pick up urban noises, such from traffic, construction, mining, sports, and cultural events. So the interesting thing is that while natural ground vibrations happen at a higher frequency of natural vibrations happen at a lower frequency of 0 to 2 hertz, artificially caused seismic vibrations from human reasons happen at a higher frequency of 5 to 20 hertz. So by tracking the changes in this higher frequency seismic vibrations, I will be able to understand the changes in above ground human activity. Luckily, the Canadian National Seismograph Network operates a network of over 200 seismic stations across Canada. And this data is readily available through the Incorporated Research Institution for Seismology, IRIS, which aggregates seismic data from countries around the world. Now, there were several seismic stations available to me, so I had to shortlist the ones that were relevant and useful to my study. So I came up with 4 different criteria. First, the proximity of the seismic stations to the city centers. Since my goal was to measure the changes in human-caused vibrations, the seismic station should be closer than 50 kilometers from a city center, so they can pick up these noises. Second of all, the seismic station should be operational before and during the COVID-19 lockdown, so I could understand the change. Third, the data should be open and available online. And finally, the seismic stations I choose should give a good geographical representation of the entire country of Canada. Using these criteria, I ended up shortlisting 9 seismic stations spread across 6 Canadian provinces from the Canadian National Seismography Network. To do my analysis and methodology, I coded in Python, and my first step was to use the OBSPy library to download the seismic data from these seismic stations in MSEED file format, which is the mini standard for the exchange of earthquake data. Once I downloaded this data, I coded algorithms in Python using the SciPython library to calculate the power spectral densities of the data, which means understanding the intensity of seismic vibrations in my data sample over different frequencies, calculated using fast Fourier transformations. Finally, I separated the higher frequency seismic vibrations caused by human activities, which is between 5 to 20 Hz, from the lower frequency seismic vibrations, which allowed me to get the human-caused seismic vibrations. I compared this from before the COVID-19 lockdown to during the COVID-19 lockdown. In my code, I use several libraries, open source libraries, including OBSPy, which is the seismic library, SciPy for data analysis, including the fast Fourier transformations, NumPy for data handling, and Matplotlib for printing out and plotting my results. And my results were very interesting. First, I found that seismic vibrations decreased during the lockdowns in all the cities of my study. After around in the middle of March, when the COVID-19 lockdown was enforced, simultaneously, seismic vibrations dropped in all my cities from 12 to 55%. In some of the bigger cities like Montreal and Calgary, the dip in vibrations was by over 50%. Another very interesting result I found was that seismic vibrations were a lot lower on weekends than they were on weekdays. In some of the cities, like Ottawa, weekends were half as active as weekdays. And this makes a lot of sense, since during the lockdowns, activities that usually draw traffic during the weekends, like malls, sports, and cultural events, were closed due to lockdown restrictions. From my results, I was able to find several main conclusions. So my first main conclusion was that anthropogenic seismic vibrations were affected during the lockdowns, and they did decrease from between 12 to 55%. I've plotted in front a diagram showing the decrease in seismic vibrations for all the cities of my study. The brighter areas represent times when seismic vibrations are higher, and the darker areas are times when seismic vibrations are lower. And it's very clear that between the lockdown period of mid-March to mid-May 2020, there was a huge seismic silence in all cities of my study. Now, my second conclusion was that seismic data can serve as a proxy for understanding the changes in human activities during lockdowns. As my results matched with human mobility trend data obtained from Apple devices by the company, as shown, and the decrease calculated by Apple matched with the decreases of human vibrations I had found for the cities of my study. Third, seismic vibrations can help understand the possible sources of human activities. Because as vibrations were lower on weekends, we can understand if whether or not malls, restaurants, and sports stadiums are actually closed during the lockdowns. And finally, my results match with results from a global study done in over 77 countries with scientists all around the world, which showed that seismic vibrations decreased by as much as 50% in countries around the world during the lockdown, which matched very well with my decrease of 12 to 55% for cities in Canada. To bridge the gap between research and policymaking, I created a web app, monitormylockdown.com, which allows policymakers and people around Canada to understand in real time the reduction in human movements during the lockdown. My web app would allow policymakers to have hard evidence to base their decisions on, and for surgical lockdowns based on time and location on areas where the lockdown may not be working. My web app can even help health workers predict spikes in COVID-19 cases and move testing equipment and open pop-up vaccination clinics in those areas where lockdowns are not working. So I'm going to give a short demo of my web app now. So here is a demo of my web app. So on the left, first you can select your city. So here, for example, I'm going to choose the city of Ottawa. The first thing my web app will tell you is the current level of seismic vibrations in that city. So here it shows that right now in Ottawa, there's only a 6% decrease in vibrations in the past month. And this makes sense, since in Ottawa during the first lockdown, the decrease was by 30%. But recently in Canada, COVID-19 cases have been dropping sharply. So many cities, including Ottawa, have been reopening and reducing the lockdown restrictions, which is the reason behind why right now the vibrations are not that low. The second thing my web app will tell you is the difference between weekdays and weekends. So here it clearly shows that weekend vibrations are a lot lower than weekdays at the current moment. Finally, my web app can even help understand the sources of the decrease in seismic vibrations. It can tell the decrease in vibrations over several different frequencies. For example, you can see the decrease in vibrations in the 5 to 10 hertz band is only by around 13%. But in the 20 to 25 hertz band, the decrease is by over 40%. And the reason behind this is that car traffic and transportation most affects the 20 to 25 hertz frequency band. I have already been expanding my project to countries around the world with rising number of COVID-19 cases like Argentina, Brazil, Poland, and Spain. And I found similar decreases in vibrations in these cities as well. So that anyone around the world can measure the effectiveness of the lockdowns in their cities, I created an open source code tutorial and free training modules that can be completed in under 3 hours, that anyone can monitor the effectiveness of their lockdowns, since in pandemic times, we're only safe when everyone is safe. To spread the word about my project, I've been giving talks and presentations about it in venues around the world, including the American Geophysical Union and the Annual Measuring Development Conference on Global Health, co-hosted by the World Bank. And my work and research has even been featured on Canadian national newspaper and national news. And I've been reaching out to policymakers such as, and I even had a 30-minute talk with the Federal Minister of Natural Resources in Canada about my project. I'm also working to expand my project in a completely different dimension. The following decade has been declared the Decade of Ocean Science for Sustainable Development by the United Nations. So to do my part, I have been working on applying my learnings of my project to oceans as well. I've been tracking underwater acoustic noise measured, and I've been measuring the reduction, using that to measure the reductions in shipping traffic during the lockdowns as well. I hope to continue expanding my projects to countries around my world so that in future lockdowns, countries are prepared to measure the effectiveness of our lockdowns and lower the cost of pandemics for better pandemic management. Thank you, and I'll be happy to answer any questions.
Thank you so much, Artash. My goodness, quite the initiative. Charlotte, could I ask you to ask, I invite you to ask the first question.
Yeah, thank you. Thank you, Artash. This is like incredibly fascinating work that you're doing. Great job. I guess my question for you, and you did touch upon it briefly, but how do you see policymakers or local or even federal governments using this information to better manage lockdowns? What do you see as it? How will the tool be used?
Well, how policymakers can use this tool? It's pretty simple. So how policymakers can use it is they can look, for example, in a province or a state, in which cities are lockdowns working, and in which cities are they not working. Because the current approach to lockdowns has been enforcing a complete blanket lockdown on the whole province or state, which is not very effective and is a very blunt approach. So these policymakers can look at which cities and which even parts of the cities are seismic vibrations not decreasing during lockdowns, to understand that in these areas, lockdowns are not effective. So instead of applying a lockdown to the whole area, they can apply surgical lockdowns to specific parts of the city or specific parts of the province where the lockdowns are not working.
Thank you.
Thanks, Charlotte. Could I invite Charles to ask the next question?
Okay, Artash, you're certainly an anomaly. You know, it's not every day you get to hear grade 9s talk the way you talk. And I congratulate you for that. And obviously, you know, you're blessed in that way. Artash, my question is about just, you know, they say garbage in, garbage out. So seismicity, I mean, I'm from the mining industry, okay? And we, in my neighborhood in Sudbury, Ontario here, every 24 hours, we're blasting, okay? And you know, obviously this creates a lot of noise, okay? And Ottawa, Toronto, wherever it is, there's a lot of construction happening, there's a lot of development happening, and there's a lot of noise that comes out of some of that. And sometimes, you know, although there's more noise when there's less traffic, simply because, you know, sometimes you want to blast or do heavy work when people are not, you know, in the vicinity. So how are you taking into consideration all the noise that's coming from other types of seismic activity in your modeling?
Yeah, that's a great question. So in fact, the goal of my project is really to understand the effectiveness of lockdowns. So this doesn't only mean looking at the reduction in traffic, for example. It means looking at the change in human activity as a whole. So all these different types of noises like mining and construction noises are all affected by lockdowns. In Toronto, where I live, during the lockdown, all non-essential construction activities were stopped. So all these noises caused by humans from traffic and even mining are definitely taken account into my project and is in fact what I'm trying to measure. Like another city in my study where mining played a big role was in Yellowknife. Whitehorse. So in Whitehorse is also a city greatly affected by mining. And during the COVID-19 lockdown, I saw a very, very sharp decrease in seismic vibrations, which I was able to attribute to the decrease in mining activities in that area.
Impressive. Thank you.
Thanks so much, Charles. Could I please invite Martin for the last question? Thank you.
Indeed, yeah, thank you, Artash. And Charlotte and Charles stole both my questions, so I'm going to quickly thinking of something else that prompted by Charles actually in terms of outliers and such. When you were sharing, I think it was Toronto, there seemed to be, a small section during the lockdown where you had a spike in seismic activity. Just wondering if you could explain that, because it's quite an outlier in otherwise nicely trending set of data points that you've got.
Absolutely, and there's two reasons behind that. And so I'll cover both of them quickly. So the first reason is that all seismic stations are currently, the whole purpose of seismic stations is really to measure natural vibrations. So it's not very often that seismic vibrations are placed in the center of cities. So in Toronto specifically, the seismic station was not as close to the city center as the seismic stations were for other cities. So obviously there would be a little bit more noise in that station. But a second thing, for that spike in general, in specific, I was able to attribute that to Easter weekend. Because since I live in Toronto, I was able to see myself that spike happened around Easter weekend. And the whole cause of that was that lockdown legislations were not really being followed during that weekend specifically. So people were going out to Hyde Park. In fact, the mayor of the city himself went down to a big park in Toronto to ask people to leave and follow restrictions, because restrictions were really not working during that week. So I think those two are very much linked.
So actually showing quite a nice correlation there. Yeah, thank you.
Thanks so much, Martin. And amazing presentation, Artash. It's fantastic to have someone from your school come and represent themselves here, and you did a wonderful job today. So thank you so much. I would like to invite Hannan Shahid, our next presenter, who is presenting Space Mining, a Dream or Reality. And so Hannan, please unmute yourself, turn on your video, and begin sharing your presentation when you're ready.
Yep. See me? Clear?
Clear.
So hello everyone. Super excited to be here talking about space mining. So I'm a graduate student at Queen's University. I'm studying mining engineering. So in the last 20 years, technology has truly advanced majorly and rapidly, with tech companies competing for humanity's first ever gold rush. Companies like SpaceX, Virgin Galactic, and Blue Origin. Is space mining still a dream, or are we in reach of it within just a few decades? Space mining could truly be the answer and solution to the extinction of resources available to us. So a bit more about me. So why do I feel connected to this specific topic? Because I'm an aerospace engineer. I'm currently studying mining engineering. I have a career vision of becoming a pilot, one day an astronaut. So I really want to explore the world, see different people and cultures, and hopefully one day go to space and see what's out there. And in hopes of helping people and humanity as much as I can. So with the global pandemic currently sending our Earth into a crisis, it didn't help with the already ongoing issues that we are facing, such as famine, food and water shortages, climate change, and running out of energy resources.
Artash, are you sharing slides, by the way? I'm so sorry to interrupt you. Or Hannan, are you sharing slides, by the way? I'm so sorry to interrupt you.
Sharing slides.
I don't know if they're visible.
Do you need to screen share?
Sure, yeah. Sorry to interrupt you, Hannan.
Is that better? Can you see now?
Yeah, can you go on present view?
Yeah. Okay, so
perfect, thank you so much, great.
Right, so as I was saying, like COVID-19 has caused a decrease in the mineral and metals that we are mining, with data showing it to be the worst hit since the 2010s, with the decrease in minerals and metals such as aluminium, nickel, iron, gold, just to name a few. Like, you're probably sitting there and thinking this is impossible. It may seem unlikely, but it isn't too far of a reach. We have already gone and built rovers that have landed on ore bodies like Mars and have already taken samples for us to analyze. If it can be done at a larger scale, to larger rocks floating around near Earth, then the result would truly be astronomical. Mining does contribute to water and air pollution here on Earth, so space mining can be the solution to that, and it can prevent the destruction of landscapes with a cleaner environment found up in space. If it does become a reality, this is a hypothetical scenario or a situation, what we can expect it to look like. It looks a bit sci-fi, but you get the big picture. So what exactly is space mining? I would say it's not rocket science, but in simple words, it is. So it's extracting minerals, metals, and other volatiles that we can expect to find from Moon, Mars, and near-Earth floating asteroids. Scientists have already reported that most of the asteroids in our solar system, the asteroid belt, and near our planet, they contain water, which can help support us being there in space. So space mining, it would work by distinguishing how accessible an asteroid or an ore body is in terms of the resources we may find from it. The best choice, of course, would be to mine the most resourceful rock, but there are many variables and factors which are required, such as the mineral processing technique, fuel efficiency, and the cost types, as well as high precision equipment and the correct gear. But lastly, the most important would be testing hypothetical situations that we can find ourselves. facing up there. So we would expect to find the following: metallic nickel iron alloys, silicate minerals, hydrated minerals, bituminous minerals, iridium, palladium, platinum, magnesium, gold, diamond, and essential volatiles like water, ammonia, carbon dioxide. So as you can see from the following images, the one on the left, that's data from NASA, where they detected minerals that were found on Mars, such as phyllosilicate, kaolinite, pyroxene, and olivine, with the highest number of exposures being from iron magnesium phyllosilicate. The Opportunity rover that was sent to Mars, it also detected clay and hydrated minerals, with hydrated minerals having the potential of supporting human life due to water properties it may contain. Other than that, scientific research also claims that the south pole of our moon, it contains water from its micrometeorites. So this topic, it correlates a little with my own research that I'm working with Dr. Charlotte Gibson on my master's project. So we're studying literature reviews and to analyze the economic feasibility of mineral processing requirements for the metals that we may find in space. I've also been sharing ideas and talking to other fellow engineers about space mining, just to get their view, what they think about it. If they think it is the future, it can be the reality. So I think it can be the future. It's possible because we already have the groundworks laid out. So I want to do my bit and progress it as much as I can. However, like the major drawbacks to this is the cost involved. So with huge amounts of funding required, there is no exact guarantee that it will work the first time round. But if it does, then the success will be huge. Also, it can create political agendas to space mining between world economies, between world countries, which can upset the system of the world. But most asteroids in our asteroid belt are nearby. They're estimated to contain quintillion dollars worth of resources. So the advantages can certainly scale up the disadvantages. So why do I think this could be the future? Like I said, we've already started our reach to becoming a space exploring civilization with NASA's OSIRIS-REx expedition, which is aiming to bring back 2 kilos of asteroid material back to Earth by 2023, which is set to cost $1 billion US. However, asteroids, it gives us the potential to create things in space. So using technology such as 3D printing, we can grab material of asteroids, create something that's never been up there, tools and machines. We can help it create rocket fuel. When water found in asteroids, it can be broken down to constituents such as hydrogen and oxygen. So we can use these elements to fuel our rockets. So far, only Luxembourg and US are the countries that are taking actions towards securing property rights for commercial companies. So with our growing population, which isn't expected to stop, we need to find a sustainable supply of natural resources. So our water-rich asteroids can create drinkable water, rocket fuel, and breathable air. Alternatively, platinum-rich asteroids, they'll create a new innovation for humanity to build green and sustainable energy to use back on planet Earth. This will also help in reducing electricity costs and any unnecessary wastages. So if you can imagine this, an entire new economy that explodes into being with new networks to be exploited. Space mining sure is hard, even for the asteroid-minded visionaries who truly believe there's a scope in this. But it's just as hard as it would have been in 1945 when engineer Vannevar Buss first proposed an idea of building a vast library of shared knowledge that people all over the world can access through their personal computers. So thank you for listening. I really hope you enjoyed the presentation, and if you have any questions, I'd be happy to answer.
Amazing. Thank you so much. Charlotte, could I invite you to ask the first question?
Yeah, thanks, Max, and thanks, Hannan, for the presentation. I suppose my question for you is, how long do you think it is, and based on what you've looked at so far, before we as humans on Earth are in dire need of space mining, of extraterrestrial exploration for minerals?
Well, like so in this decade, like so NASA's planning on going to Mars or going to Moon with Elon Musk trying to populate Mars and stuff. So I think there's already like data and stuff that shows that there's shortages for us. So I was reading the other day that we as humans, we are using up, I think, between 5 and 8 planets to survive. So I feel like as humans, we're using too much from what we already have. So I don't think it's long before we actually need to start expanding our horizon in order to find useful resources available to us.
Okay, thank you.
Hope that answers your question.
Thanks so much, Charlotte. Charles, could I invite you to ask the next question, please?
Thank you. Hello, Hannan. Thank you for the presentation. Hannan, I'm a space resources enthusiast myself, and I mean, obviously, I look way beyond space mining, as the opportunity. I think one of the words you used, which I really liked, was the word space economy. There's a whole economy out there, and not only materials, but there's energy, there's real estate, there's technology, and obviously talent and expertise. And just so you know, I'm also part of the External Advisory Council for the Western University's Institute for Earth and Space Exploration. So I talk a lot about space with many different people, and I'm always excited to hear someone as enthusiastic as yourself about it. But my very specific question is, what do you think are the linkages between space resource technologies and terrestrial mining technologies?
So are you talking about, what's the link between space mining specifically and other space technologies?
No, space mining technologies and terrestrial mining technologies. So there is mining happening on the planet. It's been happening for thousands of years, correct? And now we want to sort of look at mining in space. So my question is, what are the linkages between mining here on the planet and all the technologies and techniques we've been using, and then all the technologies and techniques that are needed for space resources?
Okay. Well, I think in space, it's definitely going to be much harder, since we have a lot of different variables to look at. So we have to look at there being no gravity. We have to look at we won't have as much water available to us. We have to look at that we won't have, let's say, it won't be as comfortable as for us to space up there and to mine up there than it is here. So I think we would have to build technologies that would kind of allow us to be comfortable being up there and using equipment to the best of our ability up in space.
Okay. Thank you very much.
You're welcome.
Thanks, Charles. Martin, could I invite you to ask the next question?
Indeed. Yeah, thank you, Hannan. It's a really interesting area. I must say, you do hope that in our lifetimes we'll see a sort of fiction becoming non-fiction in this area, to be honest. But in terms of actually getting there, you identified a number of drawbacks. Just wondering if you've got any thoughts on how we could potentially overcome some of these.
Well, I mean, there's a big capitalism on planet Earth, where the rich, they don't pay taxes and stuff. They're holding up billions of dollars of funds and stuff. So I feel like, so people like that, if they kind of believe in this project and if they're working towards it, then they'd be willing to invest to really progress us, like going beyond our horizon and stuff, and really pushing our boundaries and limits to see what we can achieve up in space.
Yeah, understood. So yeah, collaboration then, I guess, in a word. Yeah, thank you.
Thanks so much, Martin, and wonderful presentation, Hannan. It's an amazing area. So could I please invite our next presenter, Kouider, who will be discussing the overall environmental benefits of asteroid mining innovations.
Hi everyone, can you hear me?
Definitely.
Okay,
Loud and
I'll
clear.
start sharing my PowerPoint. I hope you can see it.
Yeah, I think it's good.
Awesome.
Zach, can you see that? Perfect. Yeah, I think it's good now.
Okay, awesome. So thank you everyone for attending this lecture. My name is Kouider. I've just graduated from Yale University in mining engineering. And today I'll talk about the overall environmental benefits of asteroid mining. So just to give you an idea about what we're going to be talking about today, I'll start with giving you some context, explain the goal of this study. Then I'll explain the confirmed environmental benefits of asteroid mining. After that, we'll dive into some obstacles faced, and I'll talk about the research innovations that are being developed before wrapping up. So we know that minerals are depleted on Earth. Therefore, they are harder and harder to find. They're also deeper and deeper into crust. Naturally, mining them creates now even bigger environmental disruptions. On top of that, we know that there is a serious water crisis coming. By 2025, 2/3 of the population will be under serious hydric stress. What can you do about it? Well, actually, we can mine asteroids. We know that there are a lot of water and resources out there. And also, we know that there are environmental benefits for mining water and platinum group metals. So the goal of this study would be to study the overall environmental benefits of space mining over the whole value chain and not just the extraction. So let's start with some background. There are three main asteroids of interest. The first one is the carbonaceous type, also called C-type. It's the largest type of asteroid known. There are 75% of asteroids known. And we're really interested in this type of asteroid because it contains huge quantities of water. It also contains other volatiles that can be used for propellants, also organic compounds and organic carbon and phosphorus that can be used as there are key minerals in the productions of fertilizers. The next type is the siliceous type, also known as S-type. It represents 17% of the known asteroids. This one contains a lot of metals of interest like cobalt, gold, nickel, iron, platinum, and rhodium. And the last type, but certainly not the least, metallic type. This one is very rare, but it can contain up to 10 times more metals than a siliceous type asteroid. Just to give you an idea about the scale of things we're dealing with here, this asteroid here is called the 16th Psyche, and it contains 10 quintillion kilograms of nickel iron, so that's 10 to the power 19. That's just huge. So what options do we have to mine them? We actually have three main options. The first one is to bring the raw material to Earth and process it on Earth. The second option is to bring the processed material on Earth. And the third option is to capture the whole asteroid, bring it to a safe orbit, either around the Moon, Earth, or International Space Station, and use the local resources to manufacture right there on space. Now let's talk about the mining methods. Concerning the carbonaceous type, there are two mining methods. The first one, also the easiest one to understand, is surface mining. So material is scrapped from the surface of the asteroid, either using scoop or auger, anything that can grab chunks of rocks. This is not to be used on metallic type because imagine having heavy metal flying everywhere, bad idea. And the second method is heating and also optical mining. So in heating, a simulant is introduced under the surface of the asteroid and heats it. In the optical mining method, as you can see on the video, there are giant mirrors that focus the sunlight and heats the surface of the asteroid. Then this vapor, in the two cases, is separated into the minerals of interest and waste. The minerals of interest are condensed, and they're much more easier to transport into liquid form. The other mining methods concern asteroids with large amounts of metals. This method here is called the magnetic bricks. It's a very interesting method. Basically, there is a giant magnet that's brought next to an asteroid and just recovers any loose grains of metal. The last method is used on metallic type, and it's just basically underground mining. So there is a shaft that's big, and mining can happen through that. This one is the most difficult to implement because it requires a very accurate knowledge of what's happening under the surface of the asteroid, and also very accurate engineering expertise for transportation. Okay, so I said earlier that I was talking about the whole value chain, not just the extraction. So I thought I could put this little flow chart so you can have an idea about what the value chain looks like. And this is a flow chart from when the idea first started in the 90s. It was thought to be quite simple: assess decomposition, accessibility, mining, to sell the product. Now, this is a much more recent flow chart. As you can see, it's much more complicated. There are a lot of more steps. And now we have a clear idea about how long this mission could take. It could take up to 25 years. It's 7 years only for prospecting. Okay, so now that you understand what asteroid mining is, let's talk about the environmental benefits. And there are great ones. The first one are for platinum. So we know that platinum is a very important resource here on Earth. It can be used for engineering or for medicine. However, there are only 14,000 tons of platinum left on Earth because we mined most of the reserves that are close to surface. Now they are deeper and deeper, and mining them creates important environmental disruptions. The great news is there is mining on asteroid, and also the environmental life assessment confirms that mining platinum on asteroid is actually much more sustainable than mining it on Earth. It has a much lower footprint, carbon footprint. We're talking about 267 times lower. I think this is a great news. I have a better news for you. It's water. So we need a lot of water on Earth. Great news, there are 2 trillion tons of water in the solar system. So we can just bring this water on Earth, use it for drinking, irrigation, or sanitation. Or we can use it in space. Instead of launching water from Earth to space to sustain the space mission, we can just use space water. We can use it as a chemical propellant. Can be used as steam or by breaking down the hydrogen, the oxygen, making hydrogen fuel. Or for the human missions to protect them from radiation or as a source of drinkable water and breathable oxygen. Now, cherry on top, actually using space water is much more sustainable than launching water from Earth to space. It has a 5 times lower carbon footprint. Now, this sounds great, right? But there are some serious obstacles that might make this very long term. The first obstacles are technical ones. So it's very difficult right now to identify a suitable asteroid. There still needs to be innovation and research being done to master this. The other challenges are concerning extraction. It's difficult to find enough energy and power in space to do this extraction, the mining and the processing. And it's also very consuming to use to launch this from Earth to space. So we still need to master this. And concerning the extremely small gravitational field, we can end up with uncontrolled loosened material flying everywhere, and that would be a serious safety hazard. Now, there are also financial challenges. It's very difficult to find funding for a project with such a high risk. As you can see on this graph, most of the asteroid mining have very long payback periods. We're talking about more than 10 years. And also the capital investment is huge. As you can see again on this graph, it's more than 7 years. It's more than $7 billion. There are not a lot of debt servicing arrangements that could be able to support this project. Now, say we magically found the money. Is it still economically viable? Well, we're not really sure, because there's this basic economy principle that says that whenever you increase the supply, demand falls, and automatically the price decreases. So now imagine we bring 10 quintillion kilograms of nickel iron. Is nickel iron still going to be worth what it is worth today? Probably not. How much is it going to be worth? Is it going to be worth anything? Well, we don't really know. And I talked earlier about uncontrolled loosened material. Well, just because we're trying to save Earth doesn't mean we have the right to just destroy space. That can lead to space debris and space pollution. So we need guidelines and licenses to mitigate any way that's being created. That brings us to the last challenge, the legal challenge. Frontiers are infinite, so how do we say where that everybody's responsible to start with it and who has to claim what? These are all questions we don't really have answers for and can make space mining very difficult to achieve. Okay, so I said that there are great benefits to mining on asteroids. However, it might be very long term. Climate crisis is a very urgent matter, so whichever solution needs to be taken, they need to be taken right now. The great news is there are a lot of research that are being developed because of space mining and asteroid mining that can be applied on Earth to make it more sustainable. And the first one is lower energy drilling. So for people who are not really familiar with drilling, I put this video and also this figure. So as I said earlier, a big challenge of asteroid mining is to find enough energy and power. And the great news is that now there are drilling machines that are being developed that require a lot less energy than they used to. This is great news for terrestrial mining because imagine just making operations with that use less energy and fuel and everything. They're just much more sustainable. And one of the ways to achieve this is by pre-weakening the rock before the drilling. And it can be done either with microwave radiation or by heating. Fun fact: the microwave radiation technology is being developed at McGill. The next innovation is dry systems. So usually in drilling, the drill bits are cleaned with water to clean them for dust from the cuttings, and also to cool them and to reduce the wear and tear. There is this great laboratory called Galileo Avionica that's developing dry drilling. And so the drill bit can stay sharper longer, don't need cooling to reduce the wear and tear, and the dust is cleaned with gas. And this is also great news for mining operations that happen in arid zones when there is a serious hydric stress. It can make their operation much more sustainable. So just a quick recap about what I've been talking about today. Mining asteroid can provide very interesting and great environmental impacts, especially when mining fresh water and platinum group metal. However, a mission can take up to 25 years, and seeing the obstacle that I've been explaining so far, it would take a long time before mining asteroid can happen. Climate crisis is very urgent, so we need to find solutions right now. And the great news is there are a lot of research and innovation that are being developed through asteroid mining that can make it much more sustainable, like lower energy drilling and dry systems. So now the next step would be to convince the mining companies to actually use this technology and implement them in their mining operations to make them more sustainable. So that's it from me. Really, I wanted to thank the Arthur McDonald Institute and the Iowa Entry Institute for making this competition, also my professors at McGill for sparking my interest in the subject. And this is a picture of me next to a not so small, very energy consuming equipment in a mine. So now I'm just going to open the floor for some questions. Thank you.
Thank you so much, Rem. Great presentation. And could I invite Charlotte for the first question?
Yeah, thanks, Max. And thanks, Rem. That was very, very interesting and informative presentation. Very good. At the beginning of your talk, you sort of outlined three main ways that we could mine asteroids. And the first is by bringing raw material back to Earth, and then by bringing the concentrated or refined and processed material back to Earth. And then the third would be bringing the asteroid into orbit and dealing with it and processing it in orbit. So my question for you is, given all of the work you've done to look at some of the financial and technical challenges, which of those three options do you think is the most likely to be the sort of the first way that we mine asteroids in the future?
Oh, so you're saying, are we going to bring the, so one of the three options are the closest?
Yeah, which of those three options do you think is the most technically and financially feasible?
Well, I think that bringing such big quantities of metals and resources to Earth might lead to a crash in the market. And there's also a lot of space exploration that's happening right now. So I think that maybe bringing the asteroid into orbit next to Earth, well, actually, maybe not next to Earth, but like in a safe orbit, and using the local resources to 3D print a lot of the things that are needed to do space exploration, that I think that's the closest one to reality, because it wouldn't really interfere with the market, but still would be using less resources on Earth to sustain space exploration.
Okay, yeah, thank you.
Thanks so much, Charlotte. Charles, could I invite you for the next question?
Okay. Thank you, Rem, for the presentation. And, just like the previous presentation, I had mentioned that this is an area that I have some interest in. But my question to you is, based on the research you've done, right? Where would you place Canada in this industry of space, resources? Would you maybe just give me an idea on, compared to the USA, compared to what's happening in Europe with Luxembourg, what's happening in Australia, and what's starting to happen in other countries, like, for example, Saudi Arabia. Where would you place Canada on that development continuum for space resources?
Well, I don't have an exact knowledge of it, but I think my idea would be that I know that there are a lot of like space mining exploration happening in the US, Luxembourg, and happening there. But I also know that there are a lot of research happening here in Canada, for example, in Sudbury or at McGill, where they're exploring this microwave radiation. So I think there are a lot of research that's happening, and that's good. But then again, I don't have an exact idea about the research that's happening in like other countries. I know that there are like laboratories in Europe that developing new things, in the US. So maybe like in the middle, but I don't have an exact idea. Sorry.
That's fine. That's fine. Thank you. Thank you for the answer.
Thanks so much, Charles. Martin, could I ask you to ask the last question?
Indeed, thank you. So Rim, yeah, thank you for another really interesting presentation on this topic. I guess what I was really thinking about, when you were going through the different types of asteroids and the different compositions, obviously there's going to be vastly different sizes as well. How do we go around identifying which asteroids are actually worth mining? What's the things that, how do we identify them, and what should we consider?
Well, I know that usually it depends on the orbit and also of the size and the composition. So we would want to mine asteroids for which the orbits are the closest to Earth, because then we would like save on energy to get to the asteroid, and it would also be easier to deal with them and maybe to like move their orbit. And also we want to, well, of course, mine asteroids that are like economically interesting, so that contain great resources. And we don't want them to mine, we don't want to mine very small asteroids, because then it would be like using a lot of energy and resources and not getting that much out of it. But also like mining very big asteroids is difficult. So the ideal size would be around 100 meters in diameter. So this is for the size, yeah, and the composition. I already said we want to mine like a fab asteroid that have like great resources in them.
Okay, thank you.
Thank you.
Thanks so much, Rim. Great job. So I would like to invite our final contestant, Stefan Karolidis, to present. Please unmute, turn on your camera, and share your slides when you're ready. And Stefan will be presenting.
Whoa, you guys can hear me all okay?
Yeah, we can hear you.
Perfect. Okay, where are my slides?
Stefan will be presenting the third wave of mining innovation. Whenever you're ready, Stefan.
Okay. Just load in here. Oops. Getting ahead of myself. Okay, so I'll just start by saying thank you to the Arthur McDonald Institute for hosting us today. There's been some wonderful presentations, and I guess also thank you for putting me last, because I think thematically my presentation works a little bit better, as we've seen some presentations kind of dealing with specific processes of innovation, and my presentation takes a little bit of a step back and looks like what's happening on a more macro view at the industry level. So the scope of my presentation is within the domain of hard rock mining, specifically when copper and gold mining. So let's just get a little abreast about what's happening in commodity markets. As we have exited the COVID-19 pandemic, there's been a surge in inflation in commodity prices. Central banks are still largely of the view that this inflation is transitory in nature, but nevertheless, there are some very interesting narratives beginning to form that is providing quite a bit of price support, especially as it pertains to transition metals, specifically copper. On the demand side of this, you've had many developed economies come together and outline their net zero emissions targets, typically around the 2050 to 2060 timeframe. To achieve this green recovery, there will be an immense draw on copper supplies. Just as a quick example, I'm sure you guys are all familiar with Tesla and EVs, and the demand growth for that segment is expected to grow pretty robustly. And the draw for copper for one of those EVs is 4 to 5 times that of a combustion engine car. So demand is strong. On the supply side, it's a little worrisome. Wood Mackenzie does a lot of metal research, and they forecast global mine supply to fall to just shy of 14 million tons by 2040. That's a negative 2% compounded annual growth rate over that lookout period. And there's possible disruptions along the way. So you can see that copper and gold are now sitting at multi-year highs in real terms. They kind of tested all-time highs in the midst of the pandemic, but they've kind of retreated a little bit from there. Gold prices, obviously, they're benefiting from a low rate environment we're currently in. There's currency debasement as governments are printing a lot of money to stimulate, and just an elevated risk profile as we kind of navigate the tail end of this pandemic. So the thing to keep in mind right now is miners are generating a significant amount of cash flow. They've got a lot of cash just accumulating on their balance sheets. Digging a little deeper into the supply scenario that I believe the previous lecturers talked about, yeah, it's not good. Wood Mackenzie sees a deficit in the global copper market occurring in 2025. Basically, that's just base case mine supply, the reserves that we kind of know will be mined into the future. A thing to keep in mind here is we have this big group of possible projects that could come online and kind of meet that demand. But keep in mind, a lot of these projects have been known about for a very long time. They're usually very large scale, low grade, complicated ore bodies that the economics hasn't really been able to work for them just yet. So I wouldn't kind of bet the house on these things coming along. The other thing to keep in mind with this graph too is your primary demand is growing at a constant rate here. To the extent that you believe that governments are serious about net zero emissions targets, this could be seen as a conservative estimate. So it's a bit of a dire picture, but I'm not actually that worried because I believe market forces have the potential to meet the rising demand scenarios. That's both through increase in prices of commodities and through cost out of your the cost structure of mines through technology and innovation. Now, this is how I come to the basis of that conclusion. Here I've plotted 120 years of mining innovation. The technologies listed here were basically extracted from a survey of industry professionals as game changers in the space. Basically things that once they came, you know, they didn't leave. These things are needed and necessary to mine economically. Using historical accounts, I then basically plotted each one of these technologies on a development timeline. So as things move from development, you'll get a pilot scale up, then they'll go to adoption, you'll partner with certain mines and see really kind of test the technology, make sure it has a commercial application. And then eventually these things just become ubiquitous, where if you're a mine and you're running and you're not utilizing these things, you cannot remain competitive. So the interesting things happen when you start to compare other things going on in the mining space. This is our first wave of innovation, and this one I'd like to analyze in the context of grade. At the bottom of the screen here, we have global ore grades for both copper and gold. And what you can see is they're basically on perpetual decline. This is like low-hanging fruit, basically. The highest grade stuff is mined first, and then, well, now you got to kind of make do with some of this lower grade stuff. And the challenge for industry at that point was efficiency. So you can see your mining developments, you basically put away all the picks and shovels here and replace them all with equipment, heavy capital equipment. And then the other area here is in separation and hydrometallurgy. And that's basically dealing with lower grades, coming up with chemical processes that make smaller and finer metal content in your ore liberated and processed. The next wave is better understood in the context of price. Basically in the 1970s, there's an inflationary boom. Gold reached an all-time high in real terms. And this brought a lot of smart people to the industry because there was a lot of opportunity to make immense fortunes. And here we just see refinement of the kind of the basic principles of mining. Grinding's getting a little smarter. We're introducing high pressure grinding rolls, ultrafine grinding, and your separation processes are getting a lot smarter too. So I believe now we're kind of entering this third wave, and the third wave takes themes of the last two where we're dealing with more complex ore bodies, lower grades, more complicated ore compositions, and also there's some price action happening that's kind of incentivizing further supply. And I think this wave will be highly characterized by digital investing. So this graph in the top left analyzes themes in company transcripts. So within the mining space, we can see innovation themes are being discussed way more on company calls. When companies go out and actually talk to the investors, you can see mentions of innovations have effectively doubled in a 5-year period. Compare this now to industries that we know have automated really well and cut down their cost structures like industrials and the IT space. We can see mining has traditionally been a laggard here, but just recently now they're really starting to kind of put the pedal to the metal in terms of automation, which is the keyword we're looking at here. And then this last graphic here is a survey we conducted at PDAC in 2019, where we basically asked the respondents to think about what technologies could deliver significant benefits to the space. And almost 50% said analytics was the first thing that came to mind, and close to 25% here said autonomy. So these are your digital revolutions that have previously been underapplied but are now gaining a lot of traction in the space. And we're already seeing some companies start to yield results. So keep in mind, these are major companies. So typically they have a huge portfolio of assets. So they can take on a little more risk of piloting projects at certain plants. On the mining side, we see a lot of automation in the underground and the open pit. Tech, for example, at Highland Valley Copy has seen double-digit change in key variables in terms of utilization and productivity. On the cost side, your maintenance costs are going down as wear becomes more predictable. You get a better predictive maintenance, and you don't have any scary scenarios cropping up that you kind of can't really plan for. On the milling side, it's more of an analytics story. This is taking an existing processing plan and basically getting a little smarter about it. Using an analytical software, you can look at ore characteristics as they come out in, because there's a bit of variability, and you can constantly be adjusting your reagents, your grinding time, your grinding size to get better outcomes. So we're seeing low single-digit increases in things like recovery. We're seeing double-digit increases in things like throughput. And basically what that means is you're making more for less cost. So now, let's see what this means for industry. So for that exercise, we looked at 250 mines models built and maintained by Wood Mackenzie. Of that, it's 160 copper mines and 90 gold mines. There's similar applications. Copper is usually more open pit, gold more underground. So we have to differentiate between the two. And we just assumed impacts of innovation. So we took some conservative estimates based on disclosures we were seeing so far on the companies we've been talking to. And this is what we applied. And then we used a risk adjustment factor, just taking 0.8% of kind of the low ball of what they were saying to come up with a modeled impact that then we applied to these 250 models. We also used the 10-year diffusion schedule to kind of mimic the adoption phase of what we've seen historically. So large mines with low country risk are the early adopters. They have the financial firepower and risk profile to apply these technologies. And then as you move down this gradient in terms of size and risk characteristics, you get to the end, and mine lives with less than 5 years, we just discounted them entirely. So what are the impacts? Well, here are your innovations impacts in copper. The important thing to keep in mind is over the long term, we see copper as mean reverting around the 90th percentile of cost. So basically this gray line you see right here is the 90th percentile of cost for industry. At that point, 90% of your producers are turning a profit or at the very least breaking even. So we tend to see price kind of fluctuate around that level. So now you look at the industry cost curve. This is all the production in the industry in the year of 2025. And that's the cost that production is being made at. Applying innovation benefits takes the 90th percentile of cost for copper from $2.13 down to $1.97. So theoretically, this should be deflationary for the copper price. Now, what's happening on the supply side? Well, here you can see the innovation impacts that we determined adding to the demand, the mine supply profile. And what you can see is this deficit we really only see coming on in 2026 compared to Woodmac that sees it in 2025. And even more so, there's surplus in 2023 and 2024. So to the extent you can move that here, you could see a balanced market, which means the bullish case, it may be a little bit overblown. And just to hammer point the home on deflation, we use this historical analog here of SXEW. This was a technology that basically took a bunch of mined waste that had just been sitting in stockpiles because it was too low grade to be considered economic. And when they applied it, they were able to process ore economically. SXEW eventually grew to 20% of global supply of copper. And what you saw with that was 10 years of real cost deflation. And now you can see how the copper price has kind of fallen in this period to kind of mimic that. And then of course, later you had the China boom and that one very demand driven. So now what about gold? Turning to gold. Well, it's a special case because, gold doesn't have many industrial applications. It's primarily used as a financial asset. So the incremental supply we see of 4 million ounces in, up to 2025, that's 0.1% of theoretical global supply. The World Gold Council estimates this to be 6 billion ounces held in jewelry, private investments, bank holdings, the stuff sitting in Fort Knox. So we don't expect any kind of price impact for that. But the real story here is on the cost side, because as you can cost out, you're not deflating the price of gold. So you're basically tacking all of that onto your cash margin. So we estimate the median all-in sustaining cost for industry can fall by some $25. And that's significant value creation for the industry. Running a $1,500 gold price shows around $8.2 billion of additional pre-tax cash margin, which could be a significant boon. So that's kind of the conclusion there. Third wave of innovation. If my presentation didn't convince you, the presentations before are pretty good hard facts and evidence that it's coming. It's already here in many ways in terms of both digital and automation applications. We see this as kind of, I see this as kind of deflationary from a industrials perspective, but for something like gold, there's significant room to increase value of some of these mining companies. And we believe like the original equipment manufacturers will maintain a lot of this IP, so it'll have easy dissemination into the rest of the industry. Thank you again for listening to my presentation, and I'll open the floor to questions at this point.
Thanks so much, Stefan. Could I please invite Charlotte for the first question?
Yeah, thanks, Stefan. That's, a lot of information there, really, really interesting work that you've done. I'm just trying to think of where should I start with my questions. I think I'll focus it a little bit on the mineral processing side because that is my area of experience. And so my question for you is, in your collection of data, particularly around the decreased costs or the increased throughputs that these companies have realized through implementing these different innovations. My experience has been that it can be quite difficult to actually quantify in real terms the impact of a new or innovative piece of equipment. And the main reason for this is that your processing facility is not necessarily seeing a constant feed at any given time, and there's a lot of noise in the data. So by bringing in a new piece of equipment, you might see a 0.2% increase in production. And when you see this, it's very hard to establish whether or not that was the effect of the new or innovative piece of equipment, or it just happens that your ore changed slightly and your mineralogy has changed, and that has contributed to that change to at least some extent. So my question is, how reliable do you think the data that you collected from these mining companies is? I think this is the slide here. Yeah, how reliable do you think that those percent changes are across all of these different mine sites?
So I'm not a technical guy by nature. So it sounds like you're kind of touching based on some more like of the novel processing techniques. But you can kind of quantify these things, because if you follow company reporting quarter after quarter, you will see a decrease in the cost structure. Now, obviously, that does get a little obfuscated when you have different things like, what is your production doing? Obviously, as you have more production, you can allocate your fixed costs over a greater number of units. So there are a few things. So you are kind of at the whim of the company to report good data, because as I think Charles mentioned earlier, you do run into garbage in, garbage out scenarios. But based on the breadth of reporting, we do believe that there is some science here. There is some improvement that is definitely being seen. Obviously, in the position you're in, you have to believe it's possible to go into work every day. And then, for obviously, there is some risk there. So that's why when we're actually applying these innovation impacts, we do take a risk-adjusted factor to kind of account for that. I'm trying to remain conservative in my estimates here. So that's just kind of how we account for that.
Okay, yeah, thanks. Fantastic.
Thanks, Charlotte. Charles, could I invite you for the next question?
Thank you, Stefan, for the presentation. Look, mining innovation is obviously, near and dear to my heart. Being somebody who proclaims that I actually love mining. So, I would tell you presented a lot of information here, right? A lot of information, and I think even, half the slides would have, sort of made a case for what you're talking about as well.
I like to be thorough.
But my question is, and maybe one area that you didn't touch on as much as I was looking for is, what do you think the impact of innovation is on the opening of new mines? Because obviously, I think you kind of highlighted the idea that there may be some resources identified, but at the end of the day, those resources need to become open resources, right? So what would you say is the impact of innovation on influencing new mine opening? Maybe just comment on that.
Yeah, for sure. And before I answer that, Charles, I just want to say thank you for the work you're doing at CME, because those publications you were putting out at the beginning were kind of what sparked the interest for me on my side. So thank you for publicizing some of the things these companies are doing, because sometimes they don't like talking about it. So I jumped back to this slide because you do bring up a good point. Innovation does have the capabilities to make, again, what was previously seen as uneconomic, economic. So a lot of these projects that I identified here in this green zone, they're low grade, they're complex, they're very capital intensive. They don't really work at a sub $3 copper price. But to the extent that innovation can be used to reduce the cost structure of these projects, obviously they would reduce the incentive price needed to bring this new supply online. Obviously, just mining out supply would increase the price of a commodity as you're mining less and less. So that actually is a boon too, to bring some of the supply online. But obviously, as I'm sure you're familiar, the actual permitting for some of these large scale projects takes anywhere from 7 to 10 years. So it's a short window if you want to meet this expectation with just these possible projects that maybe don't work just yet. And that's where I fundamentally believe that innovation is going to pick up a lot of the slack.
Thank you. Thank you for that.
Thanks for the question, Charles. Martin, could I invite you to ask the last question?
Indeed, yeah, thank you. Very different flavor, Stefan. So thank you for your presentation. I guess we've talked in quite loose terms really about innovation in the context of your presentation. And I think what you were saying is like the third wave of mining is really underpinned by innovation to support the third wave, or is further innovation going to be needed to carry us forward and continue to meet the world demand?
Yeah, that's a great question, Martin. I had a little bit of a deeper dive on some of these technologies in an original iteration of this presentation, but then I was cutting way too close on time. So that kind of hit the window. I'm actually going to jump to an appendix slide here that I think will highlight why I think data and analytics is so important. Obviously, if you go to a mining company, you know, their forte is not data analytics. Oh, sure. I don't know if I can present. Sorry, guys. Yeah, if you go to a miner, their forte, their specialty is not so much coming up with algorithms and data solutions that they can apply into their processing flow sheet. They're really at the beck and whim of original equipment manufacturers here. So to get an idea of the flavor of data and analytics that's being applied to equipment that is then sold to the mining space, I did a brief analysis on just the M&A history in the space, and we looked at these major OEMs. And what we found is from 2017 to 2019, over 50% of all M&A transactions conducted by these companies had innovation as the strategic imperative to do this. So what that entails is these companies buying smaller startup data-driven companies to take their core capabilities and then put them into equipment product offerings. So in some ways, miners don't really have a choice, because if you're trying to buy a mine truck 5 years from now, well, maybe the base model is an automated model. So you kind of have to work with your OEM on that. And then just diving deeper into the deals that we looked at, as you can see here, 58% of them were data-driven and 23% were automation-driven. So that's really like a very telling story where the suppliers to these miners are delivering smarter and smarter solutions. So the miners can either adapt or they can die.
No, brilliant. Yeah, thank you for your answer.
Amazing. Thank you, Stefan. So we're almost at our conclusion. The last part of this event is the judges' deliberation. So I'm going to ask Zach to set us up with a waiting screen, and I'm going to invite the judges to a breakout room for the next 15 to even 30 minutes, if it's a big debate, to decide the finalists of the competition. So thank you, everyone, and we'll see you back in 15 to 30 minutes. All right, great. We have finally found out the winner after a long deliberation. And so I'm happy to turn things over to Martin Jones to announce the top 3 in our competition so far.
Thank you, Max. And yeah, thank you to everybody that participated. You made our lives very difficult, hence the long deliberations there. The standard of presentations was excellent. It always amazes me just how excellent the presentations are, particularly given the age of some of the contestants as well. So yeah, that's really well done to everybody involved. So without further ado, 3rd place was going to go to Jinsong. Well done, Jinsong. Virtual.
Thank you very much, guys. Thank you very much. It's a great experience, and I learned a lot from your guys' presentation. It's great. Thank you very much.
Welcome. Thank you very much. 2nd place is going to go to David. Well done, David.
Thank you so much, everyone. It's been an absolute pleasure to present alongside all of you. This has been an amazing opportunity.
Yeah, thank you, David. Really well done. And then finally, 1st place, and congratulations goes to Hannah. Well done, Hannah.
I'm in shock. Thank you so much. You're all amazing.
So yeah, absolutely, fantastic, guys. Really well done, and wish you all the very best in the world final as well, Hannah. Look forward to that. So if it's all right with Max, I think I'm just going to finish off by saying a few words about the. Well, firstly, thank you very much, Max, for all the hard work, putting this competition together, the Canada final, and to the McDonald Institute as well. Really well organised. Yeah, thank you very much for that. This competition is obviously part of is run by the Institute of Materials, Minerals and Mining, and really encourage you to have a look at the website. it's there for, you know, supporting people in your industry, our industry, go through. And I think it got mentioned earlier, I'm actually the chair of the Student Early Careers Committee within the Institute. So yeah, reach out to us. You'll find our details on the Institute's website. We're always keen to get people involved and to hear from members as well. So yeah, it'd be great to hear from you guys. But yeah, hopefully you continue to follow the Young Persons Lecture Competition. Hopefully we'll see a few of you again in future years competitions as well. And hopefully you'll follow Hannah in the final, and wish her all the best.